Regression analysis is all about data. It helps businesses understand the data points they have and use them, specifically the relationships between data points, to make better decisions, including anything from predicting sales to understanding inventory levels and supply and demand.
So let's start off with this case study. Now, let's say you are conducting a survey on a bunch of college students and you'd want to understand if there's a relationship between the CGPA of the student and his or her GRE score. Now, the problem statement is basically this. So, you would understand if the students who have a higher CGPA also tend to have a higher GRE score. And similarly, if students have a lower CGPA, then would they have a lower GRE score? So, this is the problem statement. Now, to find out the solution for any problem, you need to gather data. So that is what you go ahead and do. So let's say you go to around 500 odd students and ask them their GRE score and also ask them their CGPA, and then you create a table out of this. But if you just look at this table, would you be able to draw any sort of inferences from this? Obviously no. So this is where you do some sort of data visualization. So over here you've got this GRE score and you've got this CGPA. Now, what you'll do is you will map the GRE score onto the y-axis and you'll map the CGPA onto the x-axis and you'll build a scatter plot for these two. And as soon as you build this graph, you can clearly draw inferences. So what you understand is, as the CGPA of the student increases, the GRE score of the student would also increase. So there's sort of a positive linear relationship between the CGPA of the student and the GRE score of the student. So with this, you can clearly state that if a student has high CGPA, then he'll have a high GRE score. Similarly, if the student has a low CGPA, then he'll sort of have a low GRE score. Now, this inference was quite easy to draw from this visualization. Now, what if I actually change the question? So let's say if I ask what would be the GRE score of a student if his CGPA is 8.32. Now, if you just look at this graph over here, and if I say that the CGPA is 8.32, would you be actually able to tell what would be his GRE score? Now, that would be difficult. And this is exactly where regression analysis comes in. So let's understand what exactly is regression analysis. So as it is stated over here, regression analysis basically helps us to understand the relationship between two or more variables by creating a predictive model. Now this simply means that you have a dependent variable and you have the independent variable. So as we saw in the previous graph, we had mapped the GRE score onto the y-axis and the CGPA onto the x-axis. But when it comes to regression analysis, we'll do something different. So in regression analysis, you basically have a dependent variable and one or more independent variables. Now, we will map this GRE score as our dependent variable and will map this CGPA as our independent variable. And we will try to understand how would the GRE score vary with respect to the CGPA. Or in other words, we are basically trying to understand how would the dependent variable change with respect to the independent variable. Now, since we already know the value of CGPA, which was equal to 8.32. So I would have to take this value of CGPA, plug it into the x variable, and then I'll get the value of y. So this is how regression analysis works. Now the simplest category of regression analysis is linear regression, where we basically try to understand the linear relationship between the dependent variable and one or more independent variables. And the important thing to note in linear regression is your dependent variable needs to be a continuous numerical value. So, and this is what we have with respect to our problem statement. So over here, GRE score is our dependent variable, which is a continuous numerical value. And we are trying to understand how does it change with respect to the CGPA of the student, which should be our independent variable. And when it comes to linear regression, we basically have a straight line. So a straight line is a linear equation. And that is why this algorithm is known as linear regression. So we have y and we are trying to understand how does y vary with x. So this b, what you see, so this is the coefficient of x and this is basically the slope of the line. And this a, what you see, this is the intercept of the line on the y-axis. Now let's extend this concept of linear regression to the previous problem statement. So we had the GRE score of the student mapped to the y-axis and we had the CGPA of the student mapped to the x-axis. Now we know the CGPA of the student was 8.32. So let's say if this value over here is 8.32, then the corresponding value of the GRE score of the student would be around 308 or 309. But the question over here which arises is, how do you know that this is the best fit line? Now, let's say if I draw another line like this, and the CGPA of the student is again 8.32. So for this value of 8.32, the GRE score of the student could be something else. So this time the GRE score could be around 312 or 313. So as you see, when we change the equation of the line over here, the value of y also changes. Now let's say I draw another line like this. So again, the value of x is same, but the value of y will change. So this time the GRE score would be around 305. Now, similarly, we could have a million other lines passing through these set of points. So how do you know which is the best fit line? Right. So to understand that, we'll take this example over here. So there is something known as measure of good fit. Now, instead of taking all of those points, we'll just take these set of 6 points over here. And I'll start off by drawing an arbitrary line over here. Now, these green points which you see, so these are the actual observed values for the value of x. So when the value of x is equal to 2, the observed value of y is 5. But then again, the value which is being predicted by this line would be around 2.2. So the difference between this observed value of y and the predicted value of y by this line is what is known as the residual or the error in prediction. And similarly, you'll have a residual for all of these points over here. So let's take this point now. Here the x value is equal to 2 and the observed value of y is 4, but the predicted value of y would be around 3.8. Similarly, if you take this point, x value is 4 and the observed value of y is 2, but the predicted value of y over here is 5. And if you take this point, x value is 5, observed value of y is 7, and the predicted value of y is around 6.5. Right, so these dotted red lines which you see, these basically indicate the residuals or the error in prediction. And to get that best fit line, don't you agree that we would basically have to reduce these residuals as much as possible? And this is where we have something known as the residual sum of square. So what we do is, we'll go to this first residual and we'll square this up. Then we'll go to the second residual, we'll square this up, go to the third residual, and then we'll square this up. And we'll do this for all of the residuals, and then we'll take the sum of all of the residuals. Now, when we take the sum, this has to be as low as possible. And whichever line would have the lowest value of residual sum of squares, that would be the best fit line. Now, let's extend this concept to the previous problem statement. So this was our problem statement where the GRE score was on the y-axis and the CGPA of the student was on the x-axis. And we've got these 3 lines over here. So for the first line, the residual sum of squares comes to be around 28. For the second line, the residual sum of squares comes to be around 22. And for the third line, the residual sum of squares comes to be 24. Now, when we compare all of these 3 residual sum of squares, the second line would be the best fit line for our problem statement. So now we've got the best fit line, and we already know that a linear line would have an equation associated with it, which is basically y equals mx plus c, and that is the equation over here. So over here, y is basically the GRE score of the student and x is the CGPA of the student. And these two which you see, the m value and the c value, this we've got from the best fit line. So the m value, which is the slope of the line, comes to be around 6.8 and the y-intercept comes to be 261. Now to get the GRE score of the student, all we have to do is plug in the CGPA of the student, which we already know. So we'll plug in 8.32 into this equation and we'll get a final value of 317. So this is how you are able to get the GRE score of the student by just knowing the CGPA of the student. And this is how linear regression algorithm works. Now that was a simple linear regression where we had one dependent variable and just one independent variable. Now we'll extend this concept into something known as multiple linear regression. So in multiple linear regression, we'll have multiple independent variables instead of just one independent variable. So to understand that, we'll take this dataset over here. So this is the famous empty cars dataset where we have these columns. So this is the miles per gallon column. Then we've got the weight of the car, the horsepower of the car, the number of cylinders in the car, and the number of gears in the car. And we want to understand how does the mileage of the car vary with respect to all of these other independent variables. And since mileage is our dependent variable, we'll denote it with y, and all of the other independent variables would be denoted like this. So weight, I'm denoting it with x1, horsepower with x2, number of cylinders with x3, and number of gears with x4. And this is the final equation of this hyperplane over here. So we'll type in y equals ax1 plus bx2 plus cx3 plus dx4 plus e, and this would be the equation of the hyperplane. So to implement the linear regression algorithm, we'll be working with this diamonds dataset, and let's have a glance at the description of this dataset. So this dataset comprises of 10 columns and there are 53,940 rows, or in other words, there are 53,940 diamonds. So we've got the price column, which basically denotes the price of the diamond in US dollars. Then we've got carat, which denotes the weight of the diamond. Then we've got cut, which is for the quality of the cut. So we've got all of these different columns over here. Then we've got X, Y, and Z, which basically denote the length of the diamond, the width of the diamond, and the depth of the diamond in millimeters. All right. Now, before we go ahead and start off by implementing the linear regression algorithm, let's do some data manipulation and data visualization, and let's understand this dataset properly. So I'll start off by looking at the structure of this dataset. And to look at the structure of the dataset, I'll use this str command, and inside this, I'll pass in this dataset, which is diamonds. So I'll type in diamonds over here. Right, so these are all of the columns over here. So you see that carat is a numerical column, and then we've got cut, color, and quality, which are factors. Then again, we've got numerical columns over here. Right, so this is the structure of this. So we saw the structure of the data set. Now we'll go ahead and perform some data manipulation operations. So let's say I wanted only a subset of this entire data set where the cut of the diamond is equal to premium and the price is greater than $5,000. So for that, I'll be using the deploy package. So let me load up the deploy package. So I'll type in library of deployer. And we've got the filter function from the deploy package. So I'll start up by giving the name of the data set, which is diamonds. And then I'll use this pipe operator. Now this pipe operator is used to connect different objects and functions together. So with the help of this pipe operator, I am connecting this diamonds data set with the filter function, and inside the filter function, I'll give in my conditions. So the first condition would be the cut of the diamond needs to be equal to premium. So I'll type in premium over here, and then I'll give in the second condition, which is the price of the diamond needs to be greater than 5,000. So I'll set the condition, which is price is greater than 5,000, and I'll store this in a new data set and name it as, let's say, premium price. Let me have a glance at this. So to have a glance at the data set, I'll be using the view function, and inside this, I will give in the name of the data set, which is premium price, right? So out of the 53,000 diamonds, we have extracted only 4,717 entries where the cut of the diamond is equal to premium and the price of the diamond is greater than $5,000, right? So if you look at these two columns closely, then you see that in the cut column, the value is only premium, and in the price column, it is greater than $5,000. Now, similarly, let's do some other operations. Now, let's say I want the length of the diamond to be greater than 4 millimeters. So let's go ahead and give in that command. Again, I will start off by giving the name of the data set. After that, I will use the pipe operator and then use the filter function. And inside this, I'll give the condition. So X needs to be greater than 4. I'll store this in diamonds underscore length. Now I'll have a glance at this view of diamonds length. So as you see over here, if you check this length column, which is X, you see that the length is greater than 4 millimeters. So these were some basic data manipulation operations. Now we'll go ahead and perform some data visualization operations using the ggplot2 package. So I load up the ggplot2 package. I'll type in library of ggplot2 over here. Now this dataset basically which I'm working with, the diamonds dataset, is also part of the ggplot2 package. So if you want to implement all the same code in your system, then you'd have to load the ggplot2 package first. Now I want to understand the distribution of this price column. So to understand the distribution of this price column, I'll just go ahead and build a histogram. So this is how we can build a histogram. I'll type in ggplot and I will assign the diamonds data set onto the data layer. So once the data layer is done, I'll go to the aesthetics layer and I will map the price column onto the X aesthetic. Now I am done with the data layer. So I've mapped the diamonds dataset onto the data layer and I've also mapped the price column onto the X aesthetic. Now it's time to determine the geometry. So geometry is basically the type of plot which I want to create. And I want to create a histogram. So to create a histogram, we've got the geom histogram function. Now I'll just hit enter and we've got this really beautiful plot over here. So let me zoom this. Right, so as you see, there are a large set of diamonds. So there are around more than 15,000 diamonds whose price would be less than around $1,000, right? And there are very, very few diamonds. So there would be not even around 20 or 30 odd diamonds whose price is greater than $15,000. So these were some of the simple inferences which we were able to draw by building this histogram. So now that we are done with the basic data manipulation and data visualization, we'll head on to the main part where we'll be building the linear regression algorithm. Now we want to understand how does the price of the diamond vary with respect to the carat of the diamond. So let's say if I given a carat value of around 1.3. So if the carat value is 1.3, then I'd want to know the exact price of the diamond. So this is where linear regression comes in. Now, before we build the linear regression algorithm, we actually have to divide our data set into training and the testing set. So we'll be building our model on top of the train set and we'll be evaluating the results on top of the test set. So to split the data set into training and testing sets, I would need the CA tools package. So the CA tools package gives me the sample.split function. So let me just type in sample.split over here, and this takes in two parameters. So the first parameter is basically the column with respect to which I want to split my data set, and I want to split this data set with respect to the price column. So I'll select this price column over here and I will give in the split ratio. So I'll set the split ratio to be equal to 0.75 and I will store this in a new object and I will name that object to be split tag. Now let's just wait till this command is executed. Now you guys must be wondering, why do you have to divide a data set into train and test set? So let's take this example to understand it better. So let's say you have a math test tomorrow and you haven't learned anything at all. But your friend luckily steals the question paper from the principal's room. And when you see the question paper, you see that there are 5 questions and you perfectly learn all of those 5 questions. Now there are two situations. If all of those 5 questions would appear in the exam, then you'd ace the exam. So you'll get 5 out of 5. But what if none of the questions appear in the exam? Then you'll get 0 out of 5, right? So this is what I'm trying to tell you. So we'd have to divide the data set into training and testing set. So you'd have to train your model on one particular set and you'd have to test it on another set. And if you don't do that and directly go ahead and build your model on just one particular data set, then there are very good chances that it might fail on a new data set. So this is the reason why we divide into two particular data sets. So over here, we've got the split tag. Now let me use the head function and see what is there in the split tag. So split underscore tag. Now, as you see, you just got a bunch of true values over here. So what this function basically does is it assigns 75% of the records with the true values and 25% of the records with the false values. Now, using these true and false values, we'll divide this entire data set into two parts. So for this, I'd have to use the subset function. So I'll type in subset over here. And the first parameter would be the name of the data set. And then I'll use the split tag. I'll just type in split tag over here. And wherever the value of split tag is equal to true, I will store this in a new data set and name that data set to be equal to train. Similarly, I'll use the subset function again and I'll pass in the first parameter, which is the name of the data frame. And this time I will set the split tag to be equal to false. So wherever the split tag is equal to false, I'll take all of those records and I'll store them in the test set. So now we've got the train set and the test set ready. Now let me have a glance at the number of rows in the train set and the test set. So I'll type in n row of train and n row of test. So we see that there are 42,126 entries in the train set and there are 11,814 entries in the test set. So now it's time to go ahead and build the model on top of the train set. And to build the linear regression model, we've got this lm function. So I'll just type in lm. And the first parameter is the formula where we given the dependent variable and the independent variable. So my dependent variable is price. After that, I'll give in the tilde symbol and then I'll give in the dependent variable, which is caret. So I want to understand how does price vary with respect to the caret. So whatever value is given on the left side of the tilde symbol, that will be taken as a dependent variable, and whatever values are given on the right side of the tilde symbol, all of them would be taken as the independent variables. So this is my first parameter, which is the formula. And then I'd have to give in the data set on which I'd have to build the model. So I've already told you, we are supposed to build this model on top of the train set. And I will store this in a new object and I'll name it as, let's say, linear model 1. Let me just print it out over here, linear model 1. Right, so this is what we have over here. So call, you see that we have the formula price with respect to caret, and it is built on top of the train set. And beneath that, we've got the y-intercept and the m value for this independent variable. So x is caret, and the m value or the coefficient of this caret is 7894, and the y-intercept. So y-intercept for the equation a is equal to bx would be the a value over here. So we've got the y-intercept and we've also got the m value over here. Now that we've built the model, let's go ahead and predict the values on top of the test set. So I'll type in predict. Now this takes in two parameters. So the first parameter would be the model which we've built, and the second parameter would be the data set on which we're supposed to predict the values. And I want to predict the values on top of the test set, and I will store this in, let's say, my result. So we've got the actual values and we've also got the predicted values. Now I'll go ahead and combine these two. So to combine these two, I'll use the cbind function. So the actual values are present in the price column of this test data set. So I'll just name this column as actual, and then I will create another column which is predicted, and these predicted values are coming from my result, and I will store this in final data. Now I'll have a glance at this. So view of final data. So we've got the actual values of the diamond and we've got the predicted values of the diamond, right? So let's say if this is the actual value 351, the predicted is 54. So there's a huge error in this prediction over here. Now we'll go ahead and find out the residual or the error in prediction. So that would be basically actual minus predicted. That's how we find the error in prediction. Now I'd have to convert this into a data frame first. So this is actually a matrix. So I'll use as.data frame and I'll pass final data into this. And I will store this back to final data. And once we are done with this, I will go ahead and subtract the predicted values from the actual values. So final data dollar actual minus final data dollar predicted. So I'll cut this out. I'll paste this inside these round braces, and I'll store this in a new object, and I'll name that object to be equal to error. And I'll bind this error back to the same data set. So cbind of final data, and I am binding it with error and I am storing it back to the same data set, which is final data. Right, so we've got the actual values, we've got the predicted values of the price of the diamond, and then we've got the error in prediction. So these are the individual residuals with respect to each point. Now we'd want to find out the residual sum of squares. So we have something known as the root mean square error, which basically gives us the average error for the entire model. So as it is stated in the name, root mean square error. So first we'd have to find out the square of all of these errors. So I'll type in final data dollar error. Let me cut this out and I will go ahead and find out the square of this. Now once this is done, so I have got the square of all of these errors, then I'd have to find out the mean of it, right? And finally I will go ahead and also calculate the square root of it. I'll paste it inside this and I'll use the sqrt function, right? So root mean square of error, this is what I'm finding out. And I get a root mean square value of 1221, which is actually quite huge. So this tells us that the model which we built is not actually accurate for us to give us the right results. And I'll store this in, let's say, RMSE1. So this was a simple linear model where price was our dependent variable and caret was our independent variable. Now we'll go ahead and build a multiple linear regression model. So this time we'll use multiple columns as our independent variables. So let me go to this data set and let me use the lm function again. So price again would be my dependent variable and my independent variables would be, let's say, x, y and z, which are basically the length, width and the depth of the diamond. So I'll type in x plus y plus z and I am building this model again on top of the train set. So data would be train and I will store this in linear model 2. I have built my model and I'll go ahead and predict the values. So I'll use the predict function and the first parameter would be the model which I've built, which is basically linear 2. And then I will give in the data on which I'd have to predict the values, which is new data. So I want to predict the values on top of the test set and I will store this in my result 2. I have also predicted the values. Now it's time to bind again the actual values and the predicted values. So the actual values are present in test dollar price and the predicted values are present in the my result 2. Right, now let me give them their proper names. So I'll give an actual over here and I'll also give an predicted over here. And I will store this in final data 2. So we have our new final data ready. So view of final data 2. Right, so for the second model which we've built where we had 3 independent variables, these are the actual values of the diamonds and these are the predicted values of the diamonds. Now let's go ahead and find out the error in prediction. So before that, we'd have to again convert this into a data frame. So as dot data frame of final data 2 dollar. So this just has to be final data 2 and I will store it back to final data 2. All right. Now it's time to find the error. So final data 2 dollar actual minus final data 2 dollar predicted. I'll cut this out and I will store this in error 2. Now it's time to bind the error back to the original data set. So C bind of final data 2 and I am binding it with error 2, which is stored again in final data 2. So we've got the actual values, the predicted values and the error in prediction. Now it's time to find out the root mean square error for the second model. So final data 2 dollar error 2. I'll cut this out, paste it inside this. Let me take the square of the error. Once I take the square of the error, I'd have to take the mean of it. And once the mean is also done, I'd have to take the square root of it. So I'll type in sqrt over here. Right, so this time the root mean square error comes to be around 1574. And I will store this in, let's say, RMSE2. Now let me print out both RMSE1 and RMSE2 over here, right? So for the first model, the root mean square error is 1221, and for the second model, the root mean square error is 1574. So for the second model, the root mean square error is higher. This means that the first model is considerably better than the second model. So this is how we can build multiple models and compare their accuracy with each other. So we have successfully implemented the linear regression algorithm in R language. Now it's time to implement the same in Python. And for this purpose, we'll be working with the iris dataset. So my first task would be to load the pandas library. So I'll type in import pandas as PD. Now I'll be using the read underscore CSV function. So I'll type in pd.read underscore CSV. And inside this, I'll give in the name of the file, which is basically iris.csv. And I will store this in a new object. Now I'll name that object as iris. Now I'll have a glance at the head. So iris.head, and this will give me the first 5 rows which are present in this dataset. Now this dataset is about the different species of the iris flower, which are setosa, versicolor, and virginica, and these are the different features of these species. So we've got the sepal length, sepal width, petal length, and petal width. Now for this model, I'd want to understand how does sepal length of the iris flower vary with respect to the petal length of the iris flower. So sepal length would be my dependent variable and petal length would be my independent variable. So I'll go ahead and divide this entire data set into the dependent variable and independent variable. So I will store the sepal length into y. So to do that, I will just give in the name of the data frame, which is iris, and I'll give in double braces over here and I'll put in quotes, and I'll give in the name of the column, which is sepal length. So let me just type in sepal underscore length over here. So I am extracting this sepal length column and I am storing it into the variable y. Similarly, I will extract this petal length column from the iris dataset and I'll store it into x. So I'll give in two braces over here and I will give in the name of the column, which is petal underscore length, and I am storing this into x. So I have my dependent variable and independent variable ready. Now it's time to divide these two into the training set and the testing set. So for that purpose, I'd have to import the train test split method from the sklearn package. So from sklearn dot, it would be model selection. So I'll type in model underscore selection import of train test split. So I'll go ahead and import this method from the sklearn package. Now what is done, I will use this function. So train test split, I will pass in the x value and the y value, and then I'll give in the test size. So the test size would be equal to 0.3. So this means that 70% of the records go into the train set and the 30% of the records go into the test set. And this would basically give us 4 results. So let me just type out those results. So the first result would be x train, and then we've got the x test. After that, we've got y train, and then finally we've got y test. So what are these 4 variables? So x train is basically the training set of the independent variable. Then x test is the test set of the independent variable. Then we've got y train, which is the train set of the dependent variable. And then we have the y test, which is the test set of the dependent variable. So these are the 4 results which are given by train test split. So now that we have all of these, it's time to build the linear regression model on top of the train set. So I will import the linear regression model from sklearn. So I'll type in from sklearn dot linear model. I'd have to import linear regression. So now that I import linear regression, I have to create an instance of it, and I'll name that instance to be LR. Right. So I have successfully created an instance of this linear regression model, and I'll go ahead and fit this on top of the train set. So lr.fit, and I am fitting this on top of x train and y train. Right. So we have fit this model. Now it's time to predict the values on top of the test set. So we've got the predict function. So lr.predict, and we'll be predicting on top of the test set, and I will store this in, let's say, y underscore pred. Now we've got the actual values and the predicted values. So the actual values are present in y test. I'll type in y test dot head, and then I've got the predicted values which are present in y pred. Now this is a numpy array. So I want to have a glance at the first 5 records. So this will go from 0 to 5 actually. Right, so these are the actual values of the sepal length, and these are the predicted values of the sepal length. So the actual value was 5.7. The value predicted by this model was 5.9. The actual value was 7.4. Predicted was 6.1. Then we've got 5.1, which was predicted as 4.9, right? And if we take this value 7, it was predicted as 6.15. So we've got the actual values and the predicted values. Now it's time to find out the error in prediction. So I'll load the mean square error from the metrics of sklearn. So I'll type in from sklearn dot metrics. I would basically be importing the mean square error. So now that I import it, I will go ahead and find out the mean squared error of this model. And inside this, I'll pass in the actual values which are present in y test. And then the second parameter would be the predicted values which are present in y pred. So the mean squared error comes out to be 0.19, which is actually quite less. So it seems that this model which you built is quite good.
So in linear regression, it's one of the most popular algorithms in production because it can be used for classification, it can be used for regression. It also happens to be one of the core algorithms that is used by many other algorithms. Logistic regression is a linear regression based model, right? If you take support vector machine, another very famous algorithm in data science, it's a linear model. Or if you take, if you do linear models using binned data, what you call binned data sets, then the model that you get behaves like a decision tree, right? So many of the other algorithms which are very popular in the industry, internally they're linked to linear models. You can spend your entire lifetime studying linear models. It has so much of depth and breadth that it takes a lot of time to actually get used to all these things. So today I'm going to start by introducing you to simple linear models, the core concepts, and then subsequently I'll leave some advanced discussions for the next visit where we'll be covering FMT, feature engineering model tuning. There we'll discuss some further advanced concepts of linear models. All right. So I hope these people have loaded my team has loaded the data set, everything. I'm going to give you 3 codes today, of which I'll cover 1 in the class. The other 2 is for you to go and explore further, okay? Based on what we discussed in the class. This PPT is accessible to all of you. Can you access this PPT? I think she's gone to, you can, okay. The code is also available. The PPT, the code, the data set. You should have received 3 codes. All right, let's start. As the name suggests, this algorithm is called linear regression. And the reason why it's called linear regression, as the name suggests, is it's based on the concept of a line, a plane, a hyperplane. We call it by these names. Okay. So to begin with, I need to ask you whether you know how a line is represented. Line in mathematics. Are you all comfortable with this? All right. So let's start. Imagine I give you 2 dimensions. This is x. X is one of your independent attributes. We call it columns in our data frame, right? So I have loaded a data from a table into my data frame, and one of the columns in the data frame, I call it x. This is my independent variable. The other column which I want to predict, the target column, I call it y. Could be anything. Y could be the miles per gallon, and x could be the weight of the car. The more the weight of the car, the less the miles per gallon, right? So y is my dependent variable, x is my independent variable. Imagine this x has 4, 5, 6. These are the units, 1, 2, 3, 4, 5, 6. These are the measurements of x. And let's assume, for sake of discussion, let's assume that whenever x is 1, y is also 1. So whenever x is 1, y is also 1. That is what you're seeing in the data. You take another record, there you see x is equal to 2, then y is also equal to 2. Take the third one, x is 3, y is also 3. So when you try to draw a line, a relationship between them, you see it's a straight line. The straight line tells you the relationship between x and y. How are these two related to each other? We in data science call these things as models. Models are nothing but surfaces in your feature space. What is a feature space? Feature space is collection of your independent attributes and the dependent attribute. You are trying to explore how this y and this x interact with each other That interaction is what we represented as models. So models are nothing but lines, surfaces, hypersurfaces in your feature space. So when you build k nearest neighbors, okay, in k nearest neighbors you have different classes of data points. Suppose these are different classes, okay, and okay, let me make it slightly more complex. What k nearest neighbor does is, we call it breaking your mathematical space into regions. It breaks your mathematical space into regions. So it says this region belongs to the circular point, this region belongs to the triangular point, and you have things on the wrong side. K nearest neighbors splits your mathematical space into regions. Those regions are called Voronoi regions. So this imaginary surface is the model in k nearest neighbor. So in linear regression, this line which represents the relationship in x and y, this line is my model. So I want to predict the value of y given the value of x. What the line is saying is y is equal to x. So the prediction is whenever x is some value, y will also be the same value. Can I write this expression as y equal to 1x? Does it make any difference? 1 into x. This 1 in mathematics, it has a meaning. This 1 is nothing but this angle that line makes with the x-axis, the tan of that angle into x. Whenever y is equal to x, this angle will always be 45 degrees. Okay? And in trigonometry, tan of 45 is always 1. Now you might be wondering, what is this trigonometry, tan, theta and all? These are all jargons. Actually, it's all common sense. Look at this. When we studied in school, we came across trigonometry. In trigonometry, we came across sine theta, cos theta, tan theta. What are these sine theta, cos theta, tan theta? What are these things? These are names given to certain ratios. So tan theta is, tan means the ratio between, we show it as dy by dx. How much y changes whenever x changes by 1 unit? That ratio is called tan. How much y changes when x changes by 1 unit? How much y changes in this graph when x changes by 1 unit? So 1 by 1 is equal to 1. dy by dx, how much y changes by small change in x, 1 unit change in x, that ratio is called tan theta. Sounds very hi-fi, but that's what it is. Okay? So whenever both of them synchronize, whenever x changes by 1, y changes by 1, it will always happen when this angle is 45. So we say that tan of 45 is 1. So when you say tan of 45, dy by dx will be 1 by 1, it will always be 1. Alright? Let me modify this a bit. So right now, this expression is represented as m. Okay, this is a standard practice where we represent it as m. So y equal to mx is the expression, mathematical expression of this line. Suppose I put a line here, okay, and it's parallel to this line. It's parallel to this line, okay, which means this line is also making 45 degrees to the line parallel to x-axis. I'm not going to show this line here, okay, just to make it less cumbersome. So I have another line here. This is L1, this is L2. Now can I say y equal to x? When x is 0, y is not 0, y is 2. Correct. When x is 1, Y is not 1, Y is 3. When X is 2, Y is not 2, Y is 4. So we add a constant to this. This constant is equal to 2 right now for this line. This constant is nothing but what is the value of Y when X is 0? What is the value of Y when X is 0? That is called C. It also goes by the name of intercept. Where in your mathematical space on the Y dimension, where on the Y dimension does the line intercept or cut the Y axis? So this is the generic equation of a line, Y equal to mx plus c. It tells you how Y and X are related to each other. If you look at this line L1, then this becomes 0. So Y equal to mx. If you look at L2, this becomes not 0 but 2. So this relation continues to remain same. In both the cases, the m is same. M is nothing but tan of the 45 degrees. We call it slope. Right? So this is the generic equation, one way of representing a line, Y equal to mx plus c. So in this expression, Y is given in your data set, it's the target column. X is given in your data set, it is the independent columns, the independent attributes. From this data that you have given to the algorithm has found out for you the M and the C. We call these coefficients. Coefficients of the model. This M and the C, they reflect the relationship between Y and X in your data set. So the M and the C is what forms the model for you. Shall I complicate it a bit more? We'll complicate it a bit more. Suppose instead of having 1, or let me just continue with this only. So you have one target variable Y, one X. In this case, tan of 45 happened to be 1. But suppose your line is like this. It's a straight line, but it's not at 45 degrees, it's at 15 degrees. Right? Then in that case also the equation of the line will be Y equal to mx. The reason why I'm not putting C is 0 here. C is 0. You can put C, but C is 0. And this angle M, this value of M will not be 1. It will be 1 only when it's 45 degrees. It's less than 45 degrees, so tan of 15 degrees into 1 into X plus C. This will be equation of this line. What is tan theta? Tan theta is nothing but how much Y changes for 1 unit change in X. We call it tan. Okay. All right. Let's complicate this a bit more. Suppose instead of only one variable X, now you have X1 and you have another variable X2. And you have only one dependent variable Y. In such case, the algorithm will find out the relationship between X1 and Y, X2 and Y. So it will express that relationship as Y equal to M1 X1 plus M2 X2, and there will be only one constant term, because now instead of having a line, you will have a plane. where the plane goes through the y-axis at some point, it cuts the y-axis at some point. So now you have two edges. One edge is on x2, the other edge is on x1. The two edges may have different slopes, different angles with x-axis. Those are reflected over here as m1, m2. The C continues to be the same C. Where is the plane cutting the y-axis? Which means, what is the value of y when x1 and x2 are 0? That is called the intercept.
So we're going to have only one plane, like we can't have a multiple plane, like in case of a 3D.
In case of,
like if we have a Z also, so then will be having a.
It will be called a hyperplane. We don't know how it looks, but it will be only one. Yeah. So human minds can imagine only 3 dimensions. But suppose you go beyond 3 dimensions, there also the linear models work. Those planes are called hyperplanes. Hyperplanes, how do they look? We can't imagine. So we don't know that, but they will also be one single plane. And there will be no ups and downs, no curves, nothing. It will be a straight plane. What do you mean by straight plane in 4 dimensions? No idea. It will have the same properties as the properties of a plane in 3 dimensions.
So these x1 and x2 need to be in the same plane, or it can be in a different plane, like x1 is in one plane and x2 in different plane. Is it possible?
They will be in the same plane.
Yeah.
They can't be in different. Right? And
X1 is one axis and X2 is another axis, and they are like separated with some angle.
90 degrees. This angle in linear models, this is a 3-dimensional isometric view. This angle is always 90 degrees. We say that they are orthogonal to each other. Look at this laptop. Okay, in this laptop, now this is my x1 dimension, this is my x2 dimension. There is a plane. This plane is your model. This plane is making some angle. I can't make it right now. I can't, right? It will make some angle with x1 axis. It will make some angle with x2 axis. This is my m2. This is my m1. So at what angle the plane is to x2 and x1 will decide the value of y. Okay. In this case, the value of c will be 0 because the plane is touching the y-axis. Y-axis is perpendicular like this. It's touching the y-axis at the origin, the 0 point. So imagine I can remove this. If this was a yoga tablet, I could remove this. Okay, and imagine I'm putting it in some angle, cutting the y-axis at some point. Then this angle is my m1, m2. The point at which the plane cuts the y-axis is my c. We cannot imagine beyond 3 dimensions how the planes will look, but they will have the same mathematical properties as a plane in 3 dimensions. A point that you should probably keep in mind, it will become useful to you down the line when you do deep learning and so on and so forth. The number of dimensions of a model, this is the model right now, the surface. The number of dimensions, how many dimensions is this model? 2 dimensions, length into breadth. The model is only 2 dimensions. The feature space is 3 dimensions. So the number of dimensions in a model will always be 1 less than the number of dimensions in the feature space. Right? All right. You can call it anything you like. That's not a problem. X, Y, Z. Okay, that's what they're saying. You want to call it Z, you call it Z. Doesn't matter. It just replaces the Z. Basically, these are independent variables. This is the target variable. So we are trying to understand how the target variable is influenced by these.
Say you have 3 x1, x2, x3. So how in that case the model dimension will be, so still the model dimension will be 2 only, right?
No, x1, x2, x3 are 3 independent variables. So therefore on target variables, no? So that makes it 4. 4 dimensions.
4 dimensions. What is the dimension of the model?
Model will be 3 dimension in that case. I mean, however it looks, I don't know how it will be. How will it look? It will have three edges. We don't know how it looks, so that's why we don't talk about it. But the properties of that model will be similar to properties of a plane, a line, so on and so forth.
So don't imagine, you can't.
So independent variable we have to always consider as the orthogonal in nature.
That is what the algorithms assume. All the algorithms assume that your independent variables, okay, suppose you have a data frame. In the data frame, you have multiple columns. These are independent variables, IV1, IV2, IV3, and this is my target. All algorithms assume that independent variables are independent of each other. They don't influence each other. They only influence the target. That's what they assume. But in real world, that is not true. Suppose I want to predict miles per gallon of a car, given the weight of the car, given the horsepower of the car, we know that they are related. So we can build a model, but we also know that horsepower and weight are also related to each other. More the weight of the car, more the horsepower. They're positively related, but the algorithm assumes that they are not related. This problem in linear models, it's called the problem of collinearity, where assumption is each dimension is independent of the other, but in reality they influence each other. That problem is called collinearity. Okay? This collinearity, where independent dimensions interact with each other, they are not independent. This collinearity can lead you to a problem when you productionize your models. The models may be less effective, less predictive power than required to be because of the collinearity. So one of the things that we do when building models is we see what the collinearity is between the dimensions. If the collinearity is very strong, they are very strongly related to each other, the independent variables, then we may have to resort to some techniques. Suppose this is my horsepower and this is the weight of the car, and if I plot a graph between these two, can you tell me how that will look? This is weight of the car, this is horsepower of the car. If I plot a graph between these two, take all the data points, you will see some linear trend. Okay, all of you know what is R value? Coefficient of correlation, R value. Statistics, you've done statistics, right?
Hey, go on.
Okay, R value of measurement of how these two variables relate to each other, how strongly. You will see that R value comes very close to +1 in this case. The maximum it can be is 1. So it will be very close to +1. Okay? Which means these two variables are not truly independent of each other. But the algorithm wants all the dimensions to be independent of each other. So in such cases, we resort to a technique called dimensionality reduction, which is not simply dropping the dimension. I may convert them into a composite dimension. Both the dimensions put together, I create a synthetic dimension. And I use that synthetic dimension in my model building rather than these two.
Just a question here. In this case, the horsepower and the weight of the engine is the same, almost same. Like it's increasing the same non-linear line. It means, well, if I put both of them, it will have the same effect in the model. If I remove one of them also, then it will have the same effect in the model. The model will not change anything.
If that removal is an option to you when the relationship is absolutely a line, but you will see that it's generally not a line, it's a spread, and the spread is also curved. So which one should I drop? Should I drop this or this? That depends on which dimension is more prone to errors when you're capturing the data. So instead of doing all that analysis, I might convert into a synthetic dimension using a technique called PCA, Principal Component Analysis.
One question. So in the previous example, we took two variables, independent variables x1 and x2, and they are separated by 90 degrees, right? Yeah. So in that case, we can have only 4 independent variables. Because 90, 90, 90.
No, that's what I'm saying. That is our brain. Our brain can see only 3 dimensions. but the algorithm can work in 300 dimensions. All the 300 dimensions mathematically will be orthogonal to each other.
Why is there a problem if these variables are actually very collinear and very collinear? So why is that a problem? Okay.
You please keep this question parked for a minute. I want to cover some ground before I answer that question, because that's a very important question you're asked. All right, let's move on. The term regression indicates that we're going to predict some values. Whenever you build models to predict values, we use the word regression. The term linear, now you understand where it comes from. So your linear model is nothing but a combination, addition of weighted variables. This weighted variable, this is another weighted variable, you're adding the two to predict the value of y. It's a linear combination of one or more variables with weights. The weights are called coefficients. Okay, so once again I repeat, what is this M1? M1 is how much y changes whenever x1 changes by 1 unit, keeping x2 constant. What is this M2? M2 is how much y changes whenever x2 changes by 1 unit, keeping x1 constant. Okay, so this is the relationship between x1 and y. This is the relationship between x2 and y. The relationship is how much y changes whenever input changes by 1 unit. That is a relationship, and that relationship is what we call linear models. We already seen this. I'm going to move on. So before we start building our models, we actually need to analyze our data set. And what I mean by this is, suppose this is my data set. I'll go and analyze between this IV1 and target, IV2 and target, IV3 and target, which one of these is strongly related with the target. If suppose IV2 and the target, the distribution is scattered all over the place. It's like a cloud. The data points are spread like a cloud. There's no trend you are seeing in that spread. Then in that case, IV2 is not a good predictor of the target. How can you say that? Take any value of IV2. Draw a straight line. For that value of IV2, you have multiple values of target. Which one should I take? I don't know which one to take. So we say that we say that IV2, independent variable 2, is not a good predictor of the target. On the other hand, if suppose between say IV1 and the target, we see the data points scattered in some form of a trend, then we say that IV1 is a good predictor of the target. So the first filter that you will apply in your data set is, of all the columns given to you, which columns strongly relate to the target. Those columns which don't relate strongly with the target, you are going to drop them from your analysis. You are not going to build your linear model on them. Okay? So the relationship could be positive, or the relationship could be negative. It could be downwards also. I want a strong relationship. Doesn't matter if it's this way or that way, I don't care. But I don't want to include any columns in my model which have this kind of a spread versus the y. Okay?
Sir, but it has to be linear. Like it cannot be a parabola or something like that. Suppose there exists a strong
Ideally, it should not be a parabola. It should not be parabola. Linear models are built only when you see linear relationships. If you see non-linear relationships, then you might want to resort to non-linear models. Okay, linear models, they expect a linear relationship between y and the independent variables. Then your model's predictive power will be very high. However, as you will see now, those are all very perfect conditions. In the real world, we hardly have such perfect conditions. right? So sometimes even when the relationship is not linear, we go up, build a linear model. We'll see that down the line. Okay, how do you measure the strength of the relationship between independent variable and the target? For that, we use a metric called coefficient of correlation. How these two variables, the target and the independent variable, how they correlate, how they relate to each other, which we express using a character called R. I'll tell you what this R is. This R metric can have a value of +1, -1 to +1 in this range. The least it can have is -1, the max it can have a value is +1. It cannot be beyond this range. R value can be 0. It can be 0. When you have it spread like this, your R value will be very close to 0. When you have a spread like this, your R value will be very close to -1. When you have a spread in the other way, your R value will be very close to +1. Okay, so R value is an indicator of how strong the relationships are. So let's understand this R value slightly more detailed. The formula for R value is this. This is a formula for R value, okay? So, shall we begin? Don't worry about the formula. Don't worry about the formula. Understand the concept. All the formulas are there in the library. We just need to call those functions and get our things done. But get the concept in place. Yeah.
So, if I have different units of measurement, independent and independent variables, how does the R value in that case work?
Doesn't matter. R value is a measurement based on the spread of the data. Now, have you heard of scaling? Scaling? Linear model is one model, linear regression, where scaling has no impact. Whether you scale the data or not, it's going to give the same result. All of you know the formula for variance? What is the formula, please?
Square standard.
What?
Variance.
Variance. X minus mean xi minus x bar, you can call it mu, the whole square n. Okay? I is equal to 1 to n. Let's keep it n, but otherwise we use n minus 1. If sample size is less, we use n minus 1. Okay? All of you okay with this? Don't worry about these things. What is this variance? That's what you need to understand, not the formula. Thank you. I know it's spread. What is it telling you?
It means how from the mean how the data, what is the distance of the data and how it is.
I know, but what is it telling you?
How is it related with the data?
The distance between
How it varies with how it varies. What is the similarity?
What is central value? What is x bar or what is mu? What is the central value? Don't give me the formula. Don't give me the formula. I know the formula. Central value is a value which represents all the data points that you have. Okay. So if I take all your heights, add it up, divide by a number of students in the class, that will be average height of a student in this class. Now, how good this average is? First of all, why do we take averages? Why do we need mean and median and all? Why do we do all these things? There are many. That is statistical answer. Yes, you're right. But many times in data science, you will come across a situation where you have a function and the function takes as input only one value to predict something. Now, which one of the values should I put? There are 30 students in the class, each one has a different height, right? I want to say order some kind of a code for all the students in the class, a great learning stamped code. Now, what size should I tell the manufacturer? I can't give different sizes and one unit of every size. So I have to give some size which will represent all of you so that all of you can fit in comfortably, right? That is the idea, okay? In such situations, we need to input only one value. So what we do is we find the x bar or the mu. But the question is, how reliable is this X bar? Suppose the average height of the student in this class comes to 5.5. Some of you might be 6 footers, you might get offended, you will say, boss, I'm 6 footer, how can you say I'm 5.5?
Depends upon how spread this particular, what is the difference between mean and
Exactly.
standard deviation.
So how reliable your central values is based on which you're going to do further actions. How reliable your central values is, that reliability is given by the measure of variance. If the variance is too large, the central value is not reliable, right? So the variance gives you the reliability of the central values, how reliable the central values are. So the formula for variance is this, right? Just look at the numerator. Just look at the numerator. This is the case when you have only one variable, x. Now I have two variables, x and y. I want to see how they vary together, how they influence each other, vary together. That is called covariance, which is given by xi minus x bar. We don't square it into yi minus y bar. So we find out xi minus x bar multiplied by yi minus y bar. That tells me how the data points in the feature space, they vary together. That is called covariance.
So they should not vary together to have high covariance.
Independent variables. Independent variables. Independent variables should not have covariance. Target variable and independent variable should have strong covariance. Otherwise, you don't use those independent variables. When you're building linear models, the target variable, the y, and the independent variables, IVs, should have very strong covariance. But within the independent variables, the covariance should be 0. That is an ideal situation. Practically, it never happens. All right. Now, given this covariance, now look at the formula for R. Okay. On the top, in the numerator, you are seeing covariance, right? And if you look at it carefully, the units on the top and the units on the denominator are the same. This is also xi minus x bar, this is also xi minus x, this is yi minus y bar, this is also yi minus y bar. It is squared term, but there is an under root. This is also squared term, but it's an under root. So both numerator and denominator are going to have same units of measurement, agreed? So if I have a kilogram by kilogram case, then the units cancel each other out. It becomes a unitless quantity, it is a ratio, R value is a ratio. Okay. Now, when you have a diagram, when you have a plot like this between two variables, could be independent variables, target and independent, could be anything. When you have this kind of plot, you will see that R value is close to 0. We'll see why this happens. When you have this kind of a plot where you see a trend, but as x increases, y decreases, they are going in different directions. X increases, y decreases, they're opposing each other. Then we'll have R value close to -1. Whenever they go hand in hand, when x increases, y also increases. They go in the same direction together. Then R will be close to +1. And it's not very difficult to understand why. Let's look at this particular case closely. I'm going to look at this particular case closely. Yeah, this is my mathematical space or feature space. Both x and y have some x bar and y bar, the average, right? X bar, y bar. Keep in mind, all linear models that we build, linear regression models, they will always go through the point where x bar and the y bar meet. So the linear model that we saw a few minutes ago, this model will always go through wherever the x bar and the y bar meet. It will be hinged onto that point. That point will act as a fulcrum. All right? There's one particular point that linear regression models will always go through x bar, y bar. I'm really surprised and I find it very difficult to understand why this is not told Now look at the points over here, okay? Let's look at these points carefully. Take any point, like let's take this point. For this point, what is xi minus x bar? Xi minus x bar is this distance. This is my x bar, the vertical line. Xi minus x bar is this distance. Agreed? All of you agree? What is yi minus y bar for this point? It is the distance between this point and the y bar. Agreed? Xi minus x bar is positive, yi minus y bar is positive. So when you multiply these two, it is like finding the area of a rectangle. Length into breadth. So xi minus x bar into yi minus y bar for this point is nothing but the area it covers over here. This is the area. This area is a positive area. All of you okay? Let's take another point at the bottom of the screen, say this one. For this point, xi minus x bar is greater than xi, so xi minus x bar is negative. So for this point, xi minus x bar is negative, yi minus y bar is also negative. Negative into negative becomes positive. So all the areas over here will be positive, all the areas over here also will be positive. Agreed? Take this point. Xi minus x bar is negative because xi is less than x bar, negative. Yi minus y bar is positive. So positive into negative will give you negative. All these data points will have negative areas. All these data points will have negative areas. When you total this up, sigma, you see sigma over here? Sigma means sum up all the areas. When you sum up all the areas here, all the positives and the negatives will cancel each other out. The reason why they will cancel each other out is each quadrant has same density of these points. The points are distributed like a symmetrical circle. So whenever r value is close to 0, that is because your numerator is becoming 0. Numerator becoming 0 means your distribution is like this. For a given value of x, I have multiple values of y. Which y should I take? I don't know. So we say that x is not a good predictor of y. On the other hand, if you take this plot, if it becomes tighter, then positive areas is greater than the negative areas. So r value will be close to +1. It will become 1 only when all the data points lie on a straight line, which will never happen. If this plot was this way, all the negative areas will overwhelm the positive areas, then r value will be close to -1. Right? All of you okay? So this is the concept of R value. So what we do in linear models is we test the R values of every independent dimension with the target variable. We select only those whose R value is either close to -1 or +1. Any dimension with R value close to 0, that dimension is a useless dimension. How close to 0 is useless? That depends on your particular problem statement. So generally, any R value greater than 7.7, minus or plus, it's considered as a good variable. Any variable with R value between 0.5 and 0.7, it requires further research whether this relationship is real or is it a fluke by chance that you're seeing in your dataset. Any R value close to 0, not worth considering.
What about the second case you told, fluke? What does it exactly mean? I don't understand. Why you said fluke?
Okay. It could be a sampling error. The way you selected your samples from the population, that leads to the R value. Okay. Now observe this. Since you asked this question, let's discuss this out. For R value to be 0, okay, if this is my x and this is my y, this is x bar, this is y bar, okay? X bar, y bar. I'm not showing you the coordinates. For R value to be 0, the data points, suppose I give you 10 data points, the data points have to be absolutely symmetric Symmetrically distributed for R value to be 0, absolute symmetrical distribution in all the quadrants. What is the probability that when you're doing random sampling, you'll get data points in such a way that they get symmetrically distributed around this? What is the probability? Probability is 0. That particular configuration of data points that you want from the universe, which symmetrically distributes itself around these two x bars and y bars to give you the R value of 0, that probability is 0. It'll never happen. So even in the real world, if there is no relationship between x bar and y bar, because of your sampling brings in some asymmetry in the distribution. There'll be some asymmetry in the distribution. You will end up with an R value greater than 0. This R value, we call it statistical fluke. So when R value is very close to zeros, it could be by chance sampling problem. It may not be a real relationship. So you have to go and further investigate whether the relationship is real, it might be real, or is it fake?
It might be possible also R value is greater than 70, but it might be a fluke.
Probability is very low.
Yeah, probably.
That will happen when your sampling is completely gone case. You have done some mistake in sampling. Then it can happen. All right. Shall we move on?
One question. So what is the application of this? So one thing is when we have independent variables, how they are closely related, so that we can come out with composite.
Yes. You are talking about R value.
Yeah. Another thing is finding the relationship between how independent is closely related with the target. So in both cases we can use.
Yeah, in both cases we have to use this. We have to use for both the situations to select the independent dimensions. And within the independent dimensions, knock out those which are very strongly correlated.
So is this the only Pearson only the way to find out?
No, there are other methods. Carl Pearson is the most commonly used for coefficient. There is one more available. There are many such available statistics. But this is one which we mostly use in data science, our cases. Shall we move on? Okay.
Now, this algorithm that we are going to use, what this algorithm will do is, given the data set you have, okay, suppose this is the distribution in x and y. In your data set, you have only one independent column and the one target column. And you see, notice the distribution is like this. So this is a good predictor of this y. But let me understand in precise terms, what is the relationship between y and x? I see that there is a relationship, but what exactly is that relationship? Precisely, I want that. That precise relationship between y and x will be your model, represented by a line in this case. Okay. The algorithm, what this algorithm will do is, it can find out multiple lines here. Multiple lines can be shown here, right? What the algorithm will do is, it will start with some random m and random c. Y equal to mx plus c. Y equal to mx plus c is the expression. Hey guys, I'm talking to you, not to them. Y is equal to mx plus c. So by changing m and c, whenever I change m and c, the relationship between x and y changes, which means the line changes. The line represents a relationship. So whenever I change m and c, the line will change. Okay. This algorithm will start from some random m and random c. And it will evaluate the different possible lines before it finds what is called the best fit line. Okay. Now, what is this best fit line? Amongst all the lines possible that it has checked, best fit line is that which goes through the maximum number of data points. It can't go through all of them. It goes through maximum number of data points, and at the same time, it minimizes the distance between other points and the line. The distance between other points and this line, this distance, you see the distance over here, this distance is called error. What it means is, for a given value of x, your line says the value of y should be this, but your data available in your data set is saying the value is this. The blue line here is the predicted values for the different x. Actual values are the black dots. So whenever you have a black dot above the line or below the line, That means there is a difference in prediction and actual. That difference is called error. Okay? Don't mistake the word error. Error doesn't mean anything negative, but it's used for something that you already know. I'll tell you what it is. So amongst all the different possible lines, there will be only one line which minimizes the sum of all these errors. If I sum up all these errors across all the data points, the minimum sum error will be given to you by only one line. That line is called the best fit line. The algorithm will find out for you from infinite number of possibilities the best fit line for you. It's like looking for a needle in the haystack. And to do this, it makes use of a process which is called the gradient descent. All algorithms use under the hood a learning process, a process which they make use of to find the best model for you in the given data set. That process in this case is called gradient descent.
So the errors that you're talking about, basically that will be very significant to what our alpha level is.
What is alpha level?
For example, if I'm taking that as the level of significance that I'm taking, I'm deciding for business, that I can have maybe 5% of errors there and there. And 95%
You're talking about type 1, type 2 error. That comes in classification. This is regression. However, the same concept will come into play here also in a different way. I'll tell you what that way is. Yeah. So we'll see that way. So again, once again, you have to park your question. We are too far away from those points, right? Shall I move on? Any questions?
Yeah.
So the number of points is the priority to the distance is more than the number of points, right? Listen, so there are two things you told: the maximum number of points it should go through, and also the distance. But the distance is the most priority because the errors will be less.
Yeah, error will be less when the points sit on the line, no? So it has to be taken together. Both of them are equal priority, but there's only one line which is satisfy that condition. The driving condition is the error should be minimized. That is only condition, okay? So there are no two-step process here. It's only one step. So let me explain this to you. If I plot, okay, equation of a line is y equal to mx plus c. I'm going to take one simple case, mx plus c, where in your original mathematical space you have x, you have y. One independent variable, one dependent variable. Okay. So now we have two parameters that we can modify, and whenever I modify m and c, I'll get different lines. This is m1 and c1, this is m2 and c2, this is m3 and c3. I'll get different lines. Each line has its own m and c, right? But not all lines are good lines. So if I have this line, for example, this is L1. If I take the L1 is made of M1, C1. I see that many of the data points are away from L1 on both the sides. So the error E1 is very high. If I take, say, the next one, L2, I'll call this L2, I call this L2. I see that L2 has its own slope, its own this intercept, and it also does a lot of errors, but not as much as E1, E2. I try out various lines, then I come to LBF, best fit. Best fit line is this, which has its own M, best fit, C, best fit, and E, best fit, and of all these errors, this will be the least. E best fit will be the least. Now the question is, by changing my M and C, but just a small minute amount, I'll get a different line. So there are infinite lines possible, which you will have to evaluate. Out of the infinite lines, you have to find the best fit. Brute force will not work here. You can't use brute force.
So when you talk about gradient descent, right,
See, I'm actually trying out, or say, I started with a particular MNC. And slowly I moved on. I'm correcting my errors, errors are getting reduced. All of a sudden, it again started increasing.
That will not happen, right? Except for when you cross the best fit point.
I'm coming to that now. Okay. So instead of looking at this mathematical space, I can actually look at another mathematical space, which is related to this. That mathematical space is between M and C, and this dimension is error, where error means sum of all the errors put together. Okay. In linear regression, this error is calculated as y hat, that is predicted value of y, minus y actuals, okay, raised to power 2 divided by n. N is the number of data points. I is equal to 1 to n. We call it squared error, sum of squared errors. Sum is sigma, squaring the errors. So the error done by model is nothing but a sum of squared errors. N is the number of data points you have. Isn't this formula for variance? So error is nothing but variance. How data points vary, scatter across the best fit line. The lesser the variance, more reliable the central value is. The lesser the variance of the points across the model, the better the model is. Same concept comes to you in a different way. So sum of squared errors is nothing but variance, variance of the data points across the model. So I want to find that model where the variance of the data points across the model is the least.
It's slightly confusing. See, when you say covariance, right, and you said like if you have more value of covariance, then it is better for dependent versus independent. Right?
More value R.
That is not
R is measurement of degree of covariance.
okay.
Okay. The stronger the R is, the better the predictor is.
So degree of covariance should be higher, whereas variance should be lower.
Variance in individual dimension should be low.
That is comparing with some other box model.
That is also
So always we are
degree of
You can guess this one second.
we are omitting the outliers and all. So in the data which we are collecting, we are removing the outliers. It will always in the like a group of data which is affecting the some model. So always it will be in the linear model, right?
Yeah, I didn't get your question. Come on again. Yeah, you said box plot, you identified outliers, you removed
So
the
we are removing it. So we are collecting the data which is affecting, which is going to affect the model. So if you are plotting in the any linear regression model, it will be always in the linear model.
Not necessary.
Varun, I'll take your question. I'll just hold on a minute. I'll take the question here. Within 1.96 standard deviation on this side and this side, the data points might still have noise in them, which causes a spread across the model. You're talking about outliers, which is lying 1.96 standard deviation greater. So by removing that, yes, you're cleaning the data, but within the 1.96 standard deviation, still you have noise. That noise will appear as scatter around the models. It will appear as variance around the model.
But once we are omitting the unwanted data, so it will be in the like linear regression model, but with some noise.
It will never be one single line kind of.
Actually, no, you have asked a very, very important question, which I will just answer this because this is a very important question which will be helpful down the line. Just hold on a minute. I'll answer the question first. Okay. Now, if I take any axis, any variable x, it has a spread. Okay. This spread, variance, what you call variance, there are two types of variances. One is called stochastic variance, which means nothing but probabilistic variance. The other one is called deterministic variance, which means variance that happens for reasons that I know. I know why that variance happens, okay? That is called deterministic. But variance also happens in your data set for reasons that I don't know. We call them noise. Okay, that is called noise, all right? Now, if I have a plot like this, a linear model, and I have distribution of the data points around this, okay? For a given value of x, now look at this. Actual value is this in your data set, but the model is saying it is this. Similarly, there's another actual value which is this. Why is this variance occurring? I don't know. I don't know why that variance is occurring. This is called, I don't want to use the words right now, I'll use it down the line. This variance that you see, for a given value of x, you have multiple values of y, but they're very close, but still there is a variance in them. That variance is called stochastic noise. Okay? For a given value of x, the fact that the value of y is spread around its central bar, this is deterministic. We know that this is going to be this way. All right? So when you address the outliers is something which is lying 2 standard deviations away or 1.96 standard deviation away. You're addressing the outlier, okay. But you're not addressing the random variance which exists in the data points within the 1.96 standard deviations. Those will cause a scatter of the data points across the model.
You were talking about the real actual data point or the prediction point?
Prediction is your line. Actual is the black data points. Between the actuals and line, there is a gap. That gap is my stochastic. Unexplained variance. I don't know why it happens. Yeah, in the actual data. Deterministic is, I already know my y bar has this spread and my x has this spread. This spread is also variance. I already know it has this spread. I know it will be like this only. I have no reason for worrying about that. What I'm worrying about is, for a given value of x, why are there multiple values of y?
That is stochastic. We don't know why it happens. That is what we call noise.
Is it because of lack of domain expertise? Nothing to do with
even the domain expertise, you'll have this problem.
So when we have a multi-dependent variables, right? So here we are talking about trying to find out the only one and then y. Okay, but maybe when we are we have to analyze it in the togetherness
multivariate analysis.
Maybe that is creating this kind of noise because we are trying to target only single one, right?
That can happen. That can also happen.
When the different variables actually interact with each other, there's collinearity in your data set. You can have trouble with this noise. That can happen. The noise may get cancelled out, or the noise may get magnified.
What can happen?
One more question. So we are looking for best fit line which gives us the least error.
Least sum of squared errors.
What is the definition of least? Mean
I'll tell you what is least. That's what I'm going towards now. Okay. So I have different combination of M and C. So I moved away from my original mathematical space into another mathematical space where the dimensions are the different slopes and different intercepts, different lines. Okay. Each line gives you some error. Okay. The formula for this error is the sum of squared errors, which is nothing but variance across the line. Whenever you have a squared term, this is called quadratic equation in mathematics. All quadratic equations, they have a property. The property is called, they are convex functions. Convex functions means when you plot them against their independent variables, M and C, they will always acquire a bowl shape. Three-dimensional bowl. Such functions which acquire this kind of a shape, a bowl shape in the 3 dimensions, such functions are called convex functions. They are guaranteed to have one absolute minima. Parabolic structure. One absolute minima. So for some combination of M and C, I'll get the least error. That combination of M and C, which gives me the least error, is my best fit line. So the algorithm will start from some random M and C. So maybe this is the random M and C. This is my random M and this is my random C. When I use this, I get a line, but the sum of squared errors across the line is very high. So each point here is one line in the original mathematical space. So in the original mathematical space between x and y, if this was my L1, maybe this is the L1, it had some m and some c. That m and c is this point represents this line. This line had some sum of squared errors. The sum of squared errors is this.
So you talked about one M, but if it is multiple M, still it will be like similar?
Still 100%, guaranteed.
Okay. But we can't visualize.
We can't visualize. Okay?
All right, no kidding. Let's move on. Now what this algorithm does is, it starts from some random MNC and it uses a concept called gradient descent. Descent, as the name suggests, we have to descend, okay? Gradient descent algorithm, which internally makes use of what is called partial derivatives. Partial derivatives. And this term partial derivatives, I'll tell you what it is. It's not a rocket science. It is dy by dx. It's exactly dy by dx. What it does is, for a small change in m in this direction or this direction, for a small change in m in this direction or this direction, from the first m, the random m, for a small change in m in this direction or this direction, dx, how much the error drops or increases. So when I change it in this direction, I'm going further up, the error increases, dy increases. Whereas if I go in this direction, I reduce my m, my dy decreases. So it notes down that I have to move in this direction. But you have taken only m right now. How about c? So do the same thing with c. If I increase the c slightly here, what happens to my error? If I see it slightly here, what happens to my error? I'll go in that direction where my error decreases, descent. So using this concept of partial derivatives, which is nothing but dy by dx applied on individual dimensions one at a time, that's why it's called partial. It finds out, it moves from this line to the next line to the next line to the next line until it reaches this point. At this point, what will happen is, whichever direction you move in beyond this, the error is only going to go up. Whether you go this side or that side, error is not going to come down further. So it realizes that it has reached the global minima.
This is your best fit line.
Which is the relation between M and E plus C and E.
Correct. M, C and E put together. This is the best fit line. That best fit line happens to be this line, BF.
So it does not evaluate infinite lines. It uses this gradient descent concept and finds out for the next best fit line, next, and reaches the global minimum.
So is there a chance of jumping that?
Yeah, there is.
And there can be local minimas as well in case of...
Not in quadratic functions.
So in linear regression, we'll never have local minimas.
You'll never have. If you use neural networks, you can get stuck in local minimas.
Okay.
Linear regression, the error function being quadratic, it guarantees you will reach absolute minimum. Okay, but in the process of jumping, there is something called learning step. Okay, we are too far away from this, so I'll just tell you the concept, which is used along with this partial derivatives. If the learning step, the amount of change that you do in dy and dx, if the learning step is too high, you might jump and oscillate. You might jump the global minima, go on the wrong side, and keep oscillating backward and forward, infinite loops. So the learning step is adjusted. As it keeps jumping down, the learning steps become smaller and smaller. There are various ways of handling this to prevent the oscillation. One of the ways is, as you jump towards your objective, the goal, the steps become smaller and smaller. This algorithm is called bold driver algorithm, which is part of your gradient descent, one variant of gradient descent. When you do deep learning, This partial derivatives will become very important for you to understand how the neural networks work, how the back propagation of errors happen. Those things will come into play. Okay, but we still have a lot of time before we reach there. So hopefully I'll spend some time on this one day and tell you what this is.
Both in both driver as well as gradient.
Yeah.
In both we can.
Yeah, you can, yes.
But you have various other algorithms now which have come up, which are apparently better than this. Okay, we'll talk about those things down the line. Shall I move on? All of you? Okay. Your questions are still parked, right? The two questions. What are those two questions?
One is the standard deviation, like one is talking about error data.
He doesn't, वो भूल गया तो operation
So it's basically the first one was the collinearity between that got answered. Okay. Within the variables, within the set of the dependent variables, why there should be no collinearity.
Why should there be no collinearity? What happens if there is collinearity? That was one of the questions which came up. I remember that. Good. So my strategy worked. Okay, let's move on. We'll discuss those things in detail, right? Okay. So keep in mind, we are looking at these data points closely. The distance between the actuals and the line is the predicted values. For a given value of x, the predicted value of y is the blue line. The distance between the actual, which is shown by the black dot, and the line, that distance is shown by yellow dashed lines. This distance is a measurement of error. Okay. The objective is square of these errors, all these errors squared, that sum should be minimized. Okay, which is not very difficult to conceptualize once again. So if I have my linear model drawn like this, best fit line, the data points are scattered around this. You look at the data point from this angle. When you do that, you will see a spread. This variance is called sum of squared errors, which is nothing but xi minus x bar. X bar here is your predicted lines. So formula remains same. That variance is called sum of squared errors. That variance we have to minimize. The minimal the variance is, the better your model is. All right. So let me explain this to you, because you're going to come across these terms down the line. So let me explain this to you in slightly more detail. We're looking at this model, and the distribution of the points, the red points is given to you. The blue lines are x bar and y bar. And keep in mind, your model, the best fit line, will always go through the point where x bar and y bar meet. Always. Okay. Now look at this. Don't worry about these terms. It's all, not very difficult to conceptualize, visualize. What happened? Yeah, there you go. Now, if I take the red point is the actual point in my data set. In your data set, in your data frame, there is a record with value of x, and its corresponding value y is red, the P1. But the model, the best fit line, says the value should be yellow, P2. The distance between P2 and P1, this is what we call error, the variance. This is what we call sum of squared errors. Okay, I'm showing you only one data point here, but you have to imagine there are multiple data points here. Sum of squared error applies all together. Okay, so this contributes to the sum of squared error. There is another term that we use which is called total error. Total error across all the data points put together. The total error is nothing but the difference between y bar, the expected value of y, and the actual value of y. In your data, there is a distance between the actual value of y and the predicted value, the expected value of y. Expected value is y bar. That distance is called total error. Of the total error, your model has captured this much. Your model is a regression model, hence the name given to this is regression error. Of the total error, your model has predicted this much error. Of the total error in your data set, your model has predicted this much. The difference between predicted and the y bar. This distance is called regression error. What it has not been able to explain is this. This is called sum of squared errors. Sum of squared error has another term which is called residual errors. Residuals are those things which we don't have a reason for. We don't know why they occur. They're called residuals. Sum of squared errors is also known as residual errors. So when you build these models, especially when you go to your deep learning part and all these things, you'll come across these terms. Total error is the distance between your actual data point and expected value. Okay? So if the average height of this class is 5.5, the difference between your height and 5.5 is the total error. Now you built a model to predict the height of a person in the class based on the characteristics of the person. So your model predicts some value for you. So the model predicts the height to be 5.3. Your actual height is 6. 6 minus 5.3, that is 0.7. 0.7 is the distance between, 0.7 is this distance. Your actual height minus predicted height. Right? The distance between your height and the class average, that is the total error. Okay? So you'll come across three terms: total error, sum of squared errors, and regression error. Keep in mind, regression error and residual errors, these two together is your total error. And don't mistake the word error. Error means variance. Error means variance. Of the total variance in your data set, I told you one part of the variance is caused by the deterministic, the other part of the variance is caused by the stochastic, non-deterministic. Same thing. Non-deterministic is your residual errors, sum of squared errors.
So also you told this, see, total error or regression error, not a residual, is particular to particular point, right?
No, in this case, I'm showing you only one point, but you have to imagine all the points together because this SSE, SSR, they're across all points put together. What I'm saying is what contributes to SSR and SSE. That's what I'm showing you. So you have to imagine all the points here. That becomes too cluttered. That's why I'm not showing that. What contributes to SSR, what contributes to SSE, that's what I'm showing over here.
So least error is belonging to SST, right?
Yeah. Least error is belonging to SST means?
I mean, we are talking about total error.
Total error is this. I want to minimize this. Unexplained error. That is what my objective is. The gradient descent works in finding the best fit line for you, where best fit line is that line where this error is minimized. Because I don't want a model which is not able to tell me why. I want a model which tells me why this error.
So you will not try to reduce the regression error?
No, we will not try. We will not do that. Because that is deterministic. I know why it happens.
It's because of the variance of the...
It's because of the natural variance in the process. Okay, when you're running a process, many things come into play, factors come into play, because of which the values change here and there around the expected value. That is okay with me. But for a given value of input, there are multiple values of y that I don't understand. So for given value of input, there should be only one value of y. Why are there multiple values of y? That I don't understand. That part is my unexplained error. I want a model which unexplained error is minimized. I don't want a model where unexplained error is very high. What is the use of that model? It will not predict anything.
Okay.
When you say given value of x, you have one value of y. So in this case, in this case, the P2 is that one value. That's what you're talking about.
P2 is predicted value, but you have multiple values of P1s spread around the line. That gap is unexplained. That variance is what we call stochastic, random variance. We don't know why it happens. So basically the idea is to minimize SSE, that's all. The bottom line is minimize SSE. So increase the SSR to SST ratio. That is what our objective is. Yeah. All right, let's move on. So before you build the model, you have to evaluate each independent dimension and see what is the R value. R value, coefficient of correlation, comes into play to help you identify good predictors given the target. Okay. Once you build the model, I want to see how good the model is, how reliable the model is. For that, we use another metric. That metric is called coefficient of determination. And this is represented as R square. But before you jump to it, I should caution you, R square is not always R into R. R is a coefficient of correlation. So natural to think that R square will be R into R. That is true only when you build a simple linear model between one dimension, one target. It's only true at that point. In multi-dimensional, multivariate analysis, where you have more than 2-3 dimensions, you can't say R square is R into R. Okay? So R square is just a symbol which represents another metric called coefficient of determination. How much of the total variance in your Y has been explained by your model? Keep in mind, the total variance in Y is consisting of two components: deterministic, non-deterministic, stochastic, random. How much of this total variance in your Y has been explained by your model? That measure is called coefficient of determination. Obviously, a model which explains maximal of the variance in Y, it leaves behind very small residuals, that model is the best model. So R square, it ranges between 0 and 1. 0 means your model is not able to explain anything. Absolutely useless. 1 means your model is able to completely explain all the variance in your target. There is no residual. Such models don't exist. We can never build such models. Usually R value will be between 0 and 1. The closer they are to 1, the better the model is. Because in simple linear models, it's a squared term, it can never be negative. But keep in mind, in multivariate analysis, it's not just a square term. It's something more than that. So it'll always range between 0 and 1. Are you all okay?
How much variance in Y base? Like,
if say this is 0.8,
that means your model is able to explain 80% of the total variance in your Y. Total variance, which includes stochastic and deterministic. Right? So your R square should be as close as possible to 1, your model will be good. So this metric is used to evaluate the performance of the model, while R is a metric which is used to evaluate the independent dimensions when you're building the model. Geometrically, okay, if you take one simple linear model of one X and one Y, okay, that's what I'm showing here. So this is where your X bar and Y bar meet. Please look at this carefully. This is my Y bar, this is my X bar. Okay. So there is an actual data point. Xi minus X bar is this, Yi minus Y bar is this. That gives us an area, a rectangle. We saw that earlier, right? That area represents the total variance in your data point. The total variance in this data point, the covariance in this data point because of X and Y. This is that area, the light gray area. The light gray area is this. It's behind this dark gray. Okay, the light gray area is this. That light gray area is a geometric representation of the total variance because of X and because of Y in this data point. Of this total variance, for a given value of x, your model is predicting a value of y to be this. So this predicted value of y minus y bar x bar, this dark area is the explained variance. How much of this total variance has been explained, captured by your model? R square is the ratio of the dark area to light area. What you're seeing on the top, this is the residuals, unexplained variance. So R square is again a ratio, where the ratio is between the total variance in the data points and the variance explained by your model. That ratio is called R square. Obviously, the lesser the residuals, unexplained variance, the better the model is.
So we want more R square.
Yes, exactly. But there's a problem. There's a problem here. The problem I can explain to you in simple terms.
The problem is, go back to our discussion on R, where I told you, if there is no relationship between these two, the target and the independent variable, you have to get a perfect symmetrical distribution. But the probability of getting a perfect symmetrical distribution is 0, which means you're going to get some asymmetrical distribution. The moment you have asymmetrical distribution, your R value will be greater than 0. Magnitude, this way or that way, which means R square will be greater than 0. R square is not considered as a very good metric for evaluating the models because it is easily impacted by fluke relationship. So we make use of another metric that is called adjusted R square, which is nothing but R square minus fluke. There is a formula for this. How do you find out the fluke content? Which I am going to avoid right now because it's too detailed to discuss. In case you're interested, let me know, I can share it with you. Conceptually, it's easy to understand, but the argument is very lengthy. We won't have time for that. That's why I'm going to ignore it right now. So the metric that we'll make use of to evaluate our models is adjusted R square, not R square.
But in real time, we don't calculate this fluke.
We do. It calculates, algorithm does automatically.
Automatically. We do. Okay.
We do.
The beauty of adjusted R square is, whenever in your model building exercise to predict your target, when you include useless variables which don't really have any significant impact on the target, but their relationship is statistical fluke. When you use such useless variables, R square will keep on going up and up and up. It will come closer and closer to 1. But adjusted R square will go down. It will decrease. So when you include useless variables in your model, adjusted R square will go down. It will reduce. Whereas R square is likely to go up. Adjusted R square will go up only when you include good variables in your models. Good variables are variables whose relationship is significant, strong. So we use adjusted R square for evaluating our models. One thing that you need to keep in mind, conceptually get it clear, any attribute that you use in your model building, any attribute, that attribute will always have both the components, good R and fake R. It will have both the components. But in a good attribute, the percentage of this will be very, very high compared to this. In a poor attribute, useless attribute, percentage of this and this will be almost similar. That is why when R value is close to say 0.5, 0.6, part of it will be caused by fake R, part of it will be real R. How much is real, how much is fake, I don't know. That's why it calls for further investigation before you decide to use that in your model. When R is close to 0.5, 0.4, 0.3, we don't know how much of that is fake, how much of that is real, we don't know. That's why you need to further investigate.
Before you include or exclude from your models.
How we get the explainability of the fake? Like what is actually causing fake?
Randomness in the your sampling techniques itself will bring in fake.
When you use random function to sample from population, since you asked this question, whenever you do sampling, any technique you use, clustering, layered sampling, mixed sampling, whatever you do, your sample will never be a true representation of the real population. It will never be. So its distributions will be slightly different from the distributions in the population. That change in distribution is what will introduce fake Rs.
It's only sampling which introduces fake?
Sampling is the source of this.
Okay.
Did I show you that video where I showed you universe to be under flux, continuously changing? It's never static, whereas your sample is a snapshot.
A frame in the video.
The inside and this side keep changing.
Will keep changing, right? Shall we move on? Okay.
I'm just taking you through the concepts. I'm not telling you what is the formula for all these things. They'll become too heavy for you right now. But I will eventually take you through in case you're interested. Some assumptions that this linear regression models make. We already discussed this. Assumption of linearity. The relationship between the target and the independent variables are expected to be linear. Oh, that brings me to another point. Please be careful. When your R value is close to 0, what does it mean?
Okay, I think that's what I ended up saying.
There is no linear relationship between x and y. Okay, when R value is close to 0 between y and x, that means there is no linear relationship. That does not mean there is no relationship. For example, if I give you a distribution like this is x and this is y and this is parabolic, there is no linear relationship. When you find R value for this distribution, it will come close to 0. But they are related. There is non-linear relationships. So whenever you do this analysis, R value is close to 0, go back and check your pair panels, pair plots. Is the relationship non-linear? If the relationship is non-linear and you're building a linear model on that, you're doing a mistake, a fundamental mistake. Okay? Same way, if you have a distribution like this, R value will come to 0. But there is a relationship between y and x, A sine omega t. A is the amplitude. Sine theta, you know what theta is. So when R value is close to 0, that does not mean there is no relationship. It means there is no linear relationship. If you have such attributes in your dataset, then you may have to think twice before you use linear models.
So unless we draw this pair plots, right, we will not come to know that we have this kind of non-linear relationship. So is it always suggestible to draw pair plot for each?
100%. If you ask me, I'll always say pair plot is the most important tool you have in your toolbox, which you should use to understand your data.
And suppose we got some pair plots, so we should not try those attributes at all for the model.
Try a different model, maybe a non-linear model. Okay. So now that brings me to a question: what is linear and what is non-linear? Okay. Now look at this. This is slightly funny and at the same time something which is actually serious. This y and x, okay. Mathematicians will say, if suppose this is x, this is y, and the expression is y is equal to x square. Mathematicians will say this is a non-linear function. Data scientists call this linear function. Okay. What we can replace this with some value k, so y is equal to k. So I can convert this into a linear and then build linear models on this. So when you build linear models, y equal to mx plus c, the reason why they're called linear models is these coefficients, they are not raised to the power. They're raised to the power 1. That's why they're called linear. They're linear in terms of coefficients. if I have a model like this, y equal to mx square plus c, for us, it's a linear model. Okay, so don't get confused with this. A lot of mathematicians will say this is not linear, but for us in data science, scikit-learn or R, this is a linear model. It'll show us a trend. You'll see that if you do an auto MPG case, in auto MPG case, MPG is the target, and your X is a weight of the car. You'll see that the data points are scattered like this.
You can still use linear model on this. You can still use a linear model on this.
So if R is close to 0 and if my scatter plot showing quite dispersion, so in that case I can say it's a real one. So I can remove it.
Yes.
But if R close to 0 and if there is some parabola kind of thing, in that case,
non-linear models you might have to go to. Non-linear models are models where these coefficients themselves are complex coefficients. They are not simple coefficients, they are not simple ratios. They are something like e raised to power I theta and all those kind of things will come over here.
if we have in multi-independent variable case, if one is showing linear relationship, other is in that case.
So you'll have to try both, build a linear and non-linear, see which generalizes. Finally, what is the objective? Objective is it should have minimal bias variance errors. Which one gives you that minimal bias variance error? Put that into picture. Combo is what we call ensemble techniques. In production, we never put one single model into play. We always put a multiple models grouped together in a play. We always install multiple models put together. Varun, good morning. No problem, sir. That's okay. Camera is facing me, not you. It's okay. Right? Okay. But don't knock the camera off here. He is also sleeping. Right? So what we do is, have you seen this Kaun Banega Karodpati? Have you noticed that the audience never go wrong? Now the audience individually may not have very high IQ, but put together they rarely go wrong. This concept is called wisdom of the crowd. The same concept is used in data science also. When we productionize our models, we don't put one single model into play. We always put a collection of models into play. That is called ensemble. The algorithm assumes that there is a linear relationship between independent variables and the target variable. It also assumes that there is no relationship between the independent variables. That all algorithms do. There's nothing particular about this algorithm. Assumption of normality of error distribution. This algorithm assumes that the model that you build, the best fit line would be such that the variance around the best fit line will have normal distribution. What do you mean by this? If this is my best fit line and the data points are scattered around this, and when you look at it from this angle, it will have a normal distribution. This is not guaranteed. Sometimes you end up with the best fit line, and the best fit line you might see a distribution like this, more errors on the positive than on the negative. This happens when you have outliers in your data sets. This algorithm, all algorithms will go down on their knees when it comes to outliers, but this particular algorithm is prone to outliers. If you have an outlier somewhere in your data set, the best fit line will get pulled towards that. It'll get pulled towards, it'll gravitate towards the outliers. Okay? So when that happens, the best fit line that you get, the MNC that you get, that MNC may not be the right M and C for your production. So model may perform poorly there. Okay? So when you build up models, linear models, any model, the first thing we have to do is handle the outliers first. Okay? There are various ways of testing this out, whether this is happening or not. One of the ways of testing this is you do a scatter plot between the actual values of y and predicted values of y. Okay? Between actual values of y and predicted values of y, since the data is spread around the best fit line, there should be no correlation. The distribution to be scattered like this. Predicted value of y, actual value of y, there should be no correlation between them. When there is no correlation between actual and predicted, that means your data is evenly distributed across this best fit line. Sometimes you might notice there is a trend in these errors. There is a trend, some kind of a trend. In the difference between actuals and predicted, there are trends, which means there is a trend in the residuals. As the value of x increases, the residuals increase in magnitude. When you see such trends in the residuals, that means there's something not correct with your data sets. Maybe you're having outliers, maybe you're building models on non-linear data sets. Those are kind of things which will come out. I don't know whether you heard this word, homoscedasticity of errors. Homoscedasticity, heteroscedasticity, there are two things that will come across in statistics. What it means is, as you build the model, the errors should not spread out like a cone. The spread of errors across this model, for all the range that you have, the spread should be more or less uniform. Sometimes you will see that as the value of x increases for the best fit line, the magnitude of the error increases. The spread is still normal, but the magnitude of errors, residuals, for higher value of x is different from the magnitude of errors for lower value of x, the independent variables x. Such things indicate heteroscedasticity, homoscedasticity. The expectation is it will be homoscedastic. Homo means homogeneous. Okay, so the residuals, irrespective of what the range of x is, will be similar across all the range. Assumption of independence of errors. I mean, error done in one record is no way influenced by the error done in another record. Error done on one dimension is no way influenced by the error done on other dimension. The dimensions are independent of each other. That assumption is what is usually violated. But still, we go ahead and build our models. I found a very good what you call site which discusses these errors. I've given you the URL here. By any chance you've done this Durbin-Watson test, statistics? You've done statistics, right? The inferential and this thing, descriptive statistics. Inferential statistics, you would have done z-score, z-test. You've done all the t-tests and all these things you've done, right? Okay. If you've done those things and if you remember those things, maybe you would like to visit this site. A lot of information. Please expand your horizons. Go beyond what we teach you in the class. It's just not possible to teach everything in the class for the time limit. So go beyond the whatever we teach, expand your horizons. Yeah, that is what will give you a very firm, sound footing into data science, and you'll be able to face situations confidently. So wherever I come across any URLs, any articles, I'll share those things with you on the slide. Advantages, we are still not out of the woods. There's still much more to come. We're not yet learned the full stuff, but we'll do a hands-on and then we'll see the other stuff. Advantages is very simple to implement and it's easier to interpret provided the number of dimensions is less. So when I have equation like y equal to m1 x1 plus m2 x2 plus c, I can give a physical meaning to this. I can say for every 1 unit increase in x1, how much y changes, that is given by m1. So I can physically interpret this. I can give physical meaning to this equation. You can't do this in all the cases. You may not be able to do this. Suppose you are using neural networks. You can't interpret those models. You don't know what they are. They're all black box.
Sir, what do we mean by physical definition?
I can convert this, whatever this formula is telling me, I can map it to English, right? I can tell you in day-to-day language what it is telling you. I won't be able to do that if I use, say, random forest. You're going to do ensemble where you'll do random forest. Random forest is a black box model. We don't know what it's actually doing inside. Support vector machine is a black forest. We don't know what black forest. Black forest is a pastry. Black box. We don't know what it's doing inside, right? This model is a white box. Outliers can bring it onto its knees. This particular model is prone to outliers. All linear models are prone to outliers. Decision tree is not prone to outliers. And this is a very important point. Since the linear model goes through the point where x bar and y bar meet, the best fit lines, the lines evaluated for you go through where the x bar and y bar meet. If your x bar and y bar are not reliable, then your model itself will not be reliable. So if I built a model on a dimension y and x, where this is a very large spread, the x bar is not reliable. When x bar is not reliable, how will the model which is going through the x bar, making use of this x bar, how will the model be reliable? Right? So the more time you spend in selecting your attributes to build the models, the higher the quality of the attributes that you use to build the models, the better your models will be. And the last, boundaries are linear. This is a problem not in regression, this is a problem in classification. Okay, so if we can use linear model for classification also. So if you're having a distribution of classes like this, okay, and then this, and you're trying to build linear classifiers, you'll get probably a line like this as a best fit line. So above is this triangle, below this is circles, and one triangle is. Whereas on the other hand, if you have made use of non-linear stuff, non-linear models, then probably you would have got a better result. Maybe you would have gotten something like this. Okay, so if you use non-linear models, it might do a better classification than linear models. So this limitation is not in regression, it is in classification. Let's do one hands-on. Okay, the hands-on is not AutoMPG dataset as it is given here, it's the other one, which is simplistic. So we'll start with simpler ones. The other one which I've given to you is CAR. Okay, CARPA is linear regression. I've taken the dataset directly from the UCI site. It's called imports_imports-85.data. This is the name of the data file. Okay, so instead of downloading it, I'm directly reading from there. So let me begin. Matplotlib is an instruction to the Jupyter notebook to make all the plots in the notebook itself, sorry, Jupyter server. I'm importing pandas, numpy, and from scikit-learn linear model libraries, I'm importing the linear regression. You can have linear classifiers also. Then I'm reading the CSV file which is available in this URL. It's a comma separated file, and I've taken all these column names from the UCI dataset. So that gives me the data frame which I call car_df. This is my data frame. All of you okay? So this is like loading a data into a table. So let's look at two records. Transpose is not a must, but since the number of columns is huge, I put a transpose. I'm seeing first two records, record 0 and record 1. There is obviously missing data in some of the columns. And there is string data types in other columns. Fuel type, gas, it's a string data type. Number of doors, 2, it's a string data type. All right, no problem, go down. Our objective is to predict the last column. Given all these independent variables, can we predict the price of the car? Is there a relationship between price and all these variables? That is what we want to find out. What is that relationship? But before we do that, look at the data types. Many of the data types are object. Object means string. Machine learning algorithms cannot handle string data types. They have to be converted in numbers. So what I'm doing here is, I'm going to convert into numbers, but before I convert numbers, I'm dropping some of these columns. The reason I'm dropping these columns is, If you go and take a frequency count on these columns, fuel type, for example, or engine location, for example, most of the records have only one value for this. This is called low variance filter. Look at all the data provided to you. In the data, you have columns, where in the columns there is not variance at all. There is a gender column. Gender column, all the data is about males. Then that column is useless. It's not going to give you any information. Such columns are called low variance columns. Though they are supposed to have multiple values, they have only single values, a few values. We remove them from the analysis. So when I just did this,
yeah. So do you usually do this check and get to this conclusion?
Yes. You do frequency count, then you come to conclusion.
What I did is I've manually browsed the data file. This is an Excel sheet, CSV file. You can actually see, let's do it now, why are we talking? Let's do this. What you do is, go to this site and let's download this data set. Control C, okay. Now, HTTPS, double quotes. Thank you. Now we'll save this down. We'll save it as. Let's save it as text document, and then we'll load it up. I'll just call it. Okay, where am I saving it? I'll save it on desktop. Okay. Done. Let's open it. Okay. Let's start Excel. Excel is running into problems with C. Oh God. Oh, okay. Okay. It's going to clash with their recorder. So I'm not going to open this. Let's get on to this code, but do this analysis. You'll find that these columns are having low variance filters. They're fit to be kicked out. Right? So then what I do is I saw the car data types, the column data types. Most of the data types are object, string types. I dropped my useless columns. Number of doors, most of them have 4 doors. Then fuel type, most of them are giving the fuel type as gas. Engine location, most of them is front, 1 or 2 is in the rear, so on and so forth. So once I dropped them, I'm still left with some object data type. Number of cylinders is object. And any other object data type? No, only that is object data types. Single value there, we're dropping it. Okay. Which means the current price of the car is not a function of that, it's a function of other variables. Okay, look at this. Hey guys, do you understand why we drop low variance filter? The reason why we drop low variance filter is the price is not influenced by this particular column which is low variance. If the price was impacted by this column which is low variance, then all the prices should be fixed. Right? Which means the variance in the prices is because of the other columns, not this column. So that's why we drop it. Now the number of cylinders, what I'm doing here is I'm converting all this into numbers. So wherever I come across a string called 1, I replace it with numerical 1, 2, I replace it with 2, and so on and so forth. You should do this with care. Okay. You should do this with care. Suppose you had a column called gender and the gender was male and female. Then I cannot do this blindly like this. Because if I replace a gender, say a male with 0 and a female with 1, then I'm introducing an order in that column. That's called ordinal columns. 0 is less than 1. But there's no such relationship in the real world. So if you have a gender column, then I will use a technique called one-hot coding. One-hot encoding. I will use that technique to replace my strings into numbers. That example I have given you in AutoMPG dataset. Okay, you look at that later. Okay. On the other hand, if I have a column called income group, where they have income groups like low, middle, high. Now there I can go and replace low income group with 0, medium income 1, high income group 2. Because the same order which exists between 0, 1, 2 exists in that column also. Okay. So if your column is an ordinal data type, you can go and introduce order in your numerical values. If the column is not ordinal, gender column, then you cannot blindly convert them into 1 and 2. You have to resort to one-hot coding. In scikit-learn, there's a facility function called label encoder. Label encoder introduces order in your data. So be careful when you're using that. Instead of using label encoder, use one-hot coders.
All right. Everything has a but. Yeah.
Before dropping this variable, we have to convert it to level encoder or one.
Which variable?
We dropped all of the variables.
Not necessarily. Since we're going to drop, why do you need to convert?
Then how will we check the values of this?
I manually check. Frequency problem.
I just did like car underscore def not really so it showed some of the values which have the integers, which are only integer or float.
Yeah.
I didn't check the character. So that we have to convert to
that. If you want to do it here, then
so basically you did the background job and then fine.
Shall we move on? Okay.
So be careful when you're converting your object data type into numbers. Don't end up introducing any order which doesn't exist. So when you use one-hot coding, have you all seen one-hot coding anytime? You're not seen one-hot coding? Okay, I'll tell you what one-hot coding is, then we'll move on. Sorry, you have a column gender, and the gender column has male and female, okay? This I cannot use as it is in my modeling. So what I do is I convert this into numerical data types. All data types should be numerical. So when I convert into numerical, I use one-hot coding. What will happen is, it'll replace this gender column with two columns, gender underscore M, gender underscore F. Okay. Wherever the record is M, you will have 1 here, 0 here. Wherever the record is female, you will have 1 here, 0 here. So this column will be dropped. In your data set, you will be left with this column. 1 and 0 will be stored on the hard disk or in wherever you're storing it as numbers.
Numerical values.
Okay. In last class we had used this category.
Can you just name this?
Yeah.
We used what?
Category or something.
Label encoder we used. We just manually converted. We didn't use the scale or category. Last time we just converted to category and then we changed it to 0 and 1.
0.
But we didn't use level encoder and 1 or encoder.
Be careful when you're doing this.
You see, level encoder is something like it will do a sequencing 1, 2, 3, 4, 1, 2, 3 as per the number. But what happens if you see like cities, let's say we count 2, 3 cities, it doesn't have 1, 2, 3. If you have like let's say
Bore and stroke is right now object. So I'm dropping these data types. Okay. And here car data types, let's say again, bore and stroke is still object data types. Okay. Here I'm converting my cylinders into numerical data types. And here I'm converting my data types into this thing, float. Okay. Guys, all of you with me on the cylinders till cylinder point. Okay. After cylinder point, what I've done here is based on the experience I had in the other data set, where there were missing values. In AutoMPG dataset, you'll see missing values. Okay, so what we do is, if we come across any missing values, replace it with nan. Nan means not a number, null values. Okay, so what I'm doing here is car underscore df dot replace wherever we come across with some question mark, replace with nan. But I didn't find any question marks in this dataset. The question marks were there in AutoMPG dataset. Okay, so we can actually delete this line. We don't need it. Then at this point, what I'm doing is, there are question marks there. Oh yeah, sorry, there are question marks there. Correct, we saw it here, right? We saw it here. Question marks here, sorry, mistake. There are question marks here. These question marks now would be replaced with not a number, null values. Okay, when you replace question marks with null values, you can do numerical Python operations on it and convert into appropriate values. Okay, that's why we did this. Move on. My data types right now are, after changing the data types here, after dropping the columns here, some of the data types are still object. Object means string data types. So what I do here is I first convert my cylinder into numericals. Then I change my data types here. Look at this. car_df bore, I replace that with as type float. I replace stroke column as type float. So I'm changing all the data types to float. Because many of these columns, let's say which column had that question mark, normalized losses. Normalized losses. It's already a numerical column, I think. Yes, it is already a numerical column. So I don't need to change it. There you go. It's already a numerical column, so I don't need to change it. Rest of the columns which are object data types, I'm changing into float types. Till this point, is it okay? Once I've changed the data types to numbers, numerical, I know there are many missing values. So the strategy I'm using here for missing values is replace the missing values of price column with the median of the price column. I want to explain this step to you. So I have a data frame, and in this data frame I have one column. This column is called price. In this column there are many NAs. NA. Wherever there are question marks, we replaced all of them with NAs. The question mark has been left behind by the data entry operator because when he was entering the data, he did not have values for those columns, those records. Okay. So we replaced question marks with NAs, all this became NA. Because now these have become NA, I can use the function fill NA. What this function does is, if you see that syntax, what I've done is find out the median of this column. Whatever values are available, using those values, find out the median. Replace the NAs with the median of this column. It is always safer to replace missing values with missing values with median, because means they are easily impacted by outliers. Mode is used in categorical variables. We are running with float variables. So we always replace mean or median, but we are not yet check the outliers. All columns will have outliers. Mean get easily impacted by outliers. So if you replace these values with mean and go and remove the outliers, then these values will be completely incorrect. So replace with median. Median is not impacted by outliers, right? And the beauty of this is, in scikit-learn, I can find median of even an object column. The column is supposed to be numeric, but because it has question marks, the data frame has converted into an object data type. But you can still go ahead and find the median of that column. Why? Because median is physical central value. Mean is mathematical average. It's a calculated central value. You cannot find mean of an object data type. You can find median of an object data type. Right? All of you getting the difference? That is where the difference between Python and R comes. In R, I will have to first convert into numerical value even to find median.
Sorry, so as a thumb rule, can we say that always there is median?
No. Now, how do you address missing values? Okay. How do you address missing values depends on your analysis of the data and why the values are missing. The values can be missing because of some random reasons. We call it randomly missing values. Values which are randomly, you don't see any patterns in them. They're missing values in all records in all columns, randomly distributed. Then we say that data is missing at random. There's no particular reason for it. Okay, whereas there can be situations where the values are missing because of some reason. They are not because of randomness. For example, if you take income, usually you will find nobody wants to disclose their income. So you'll find missing values in that income column, many of them. So depending on what is the reason for that missingness, you'll apply different strategies. If it is income column where the values are missing because of the nature of the column, then I might have to build a sub-model, a model inside a model, where I predict the values of the income based on the other attributes available. So my domain knowledge will come into play, which will help me understand what are the other attributes that this income column is going to rely on, depend on. How can I guess it? So whenever I create such imputed values, as we call them, I'll create a new column, income imputed. So I will not touch the original column. I'll create a new column called income imputed, where all the data available is copied as it is, including the missing values, and the missing values are imputed from the other columns. That is one strategy. If your data is missing at random, then replacing the column with a median is the default strategy we use. Look at the spread of the data on that column. If you see long, thin tails, mean is not reliable. So we replace with median. Right? There is a package available called mice. It's available both in R and Python. In Python, it is available in another package called stats model. Stats model. Mice stands for multiple imputations through chained equations. Multiple imputations through chained equations. Yes. When you run this package on your data set, it will automatically try to replace the missing values in all the columns with predicted values where predictions will be based on the other columns. It will establish the relationship, it will see which one is strong relationship, it will go and impute. So one column's missing value might be imputed multiple times from multiple columns. Please go and read about this. It's a very powerful package. When something comes with power, you have to be very careful in using it. So read about this mice. I'm not going to cover it here, but it's a very beautiful package. You should read about this. And just to add to the confusion, apparently the mice implementation in Python is slightly different from mice implementation in R. Now they both call it mice.
Suggest a lot of things also. Low variance in automatic drop. Nice.
So these are the tools that you should be aware of, you should have in your portfolio when you start doing data science projects. All right, all of you on this? Shall we move on? Once I've done this, then I go and do my basic statistics, diff, describe with descriptive statistics, and you know how to interpret this? All of you are aware of this? Take any column, say height of the car. First thing you should look at is difference between mean and median. The mean is 53.72, median is 54, not a very big difference. 53.72 and 54.10, not a very huge difference to worry about. Look at the distance between the length of the left-hand tail and the right-hand tail. Left-hand tail is minimum minus first quartile. 47.8, let's take it as 48, 48 and 52, that's around 4 units. 4 units. Difference between this and this is again 4 units. So it's going to be a very symmetrical bell curve. The distribution is likely to be a symmetric bell curve for height. All right, I don't see any skew to worry about. Look at the car weight. Same story repeats here. 2555, 2014. If there is any column where the mean and median are very different, then you might be having a skewed data set. Look at this one, price. Now price is the target, forget the price. Let's see if our analysis stands. Let's see whether it stands, okay? So this is a numerical way, a statistical way of analyzing data, but instead you can do a pair plot. In pair plot, I always prefer to have the diagonals in form of density graphs. How do you get that? When you call the pair panel, you give diagonal kind is KDE, kernel density estimates. When you do this, you get the plot like this. Now let us spend some time on this. Always keep in mind, the output of the pair plot is a square matrix. It has as many rows, as many columns it has, okay? So this is rows versus rows comparison. So we have normalized losses, then we have wheelbase, we have length, so on and so forth. What I've done is from car DF, I have taken using index locator all rows column 1 to 16. Yeah, column 0 is my column 1 to 16. How many are there here? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have not taken the price column here. So what we do here is, instead of doing this, you do this. You do this. Just comment this out. Okay. SNS.pairplot car underscore df KDE. You do this. We'll do this pair plot. Now we run this. So let's let it plot. Fortunately, it's coming out fast. Yes, sir. Got it. Now I want to make sure my price column is reflected here. We're going to predict the price, right? So price column is, I think, second last or something. Cylinder MPG it's last but one. Why is it not showing to me? I'm not getting it. One second, I probably didn't. Car underscore df diagonal. Are you able to get the price column? No, it's there in the data set. It's there in this price. There you go. Car underscore df describe, it's there in this data set. But you guys are getting it? All right, okay. Let's look at that. Okay. The first thing that you need to do is, when you do pair plot, is first thing that you need to understand is first row and first column is same, second row and second column is same, third row and third column is same, so on and so forth. Okay. And when I do a comparison of a column with itself, if I do a comparison of, say, MPG versus MPG, what kind of a plot will I get? Scatter plot? It will be a straight line. There will be no information here. There's no spread, nothing. So trying to do a scatter plot for a column with itself is useless. It's not going to give you any information. So whenever it comes to that point where you are going to look at a column versus itself, what they have done is, instead of giving you a scatter plot, they have given you a density curve. By default, they give you histograms. We have changed it to density curve. The advantage of doing that is, in R, if you do this pair plot, it will leave out the diagonals as blank. It will leave out the diagonals as blank. It will not show you anything there. Whereas what happens in scikit-learn is, they give you a distribution. Why leave it blank? Use it to show the distribution on that particular column. Okay. So that is why diagonals, you will see the distributions, how data is distributed on that particular column. Okay. So let's look at the diagonals. In the diagonals, in my case, first column is symboling. Honestly, I don't know what symboling is. Maybe I should have done that homework. Next column is wheelbase. Wheelbase is basically how spread the front wheel and the back wheel, the distance between them. Okay, we see a normal distribution, except for higher values. Higher values, there seems to be some kind of a tail. Doesn't look worrisome. Look at the length of the car. Again, almost a normal distribution. But we see some kind of overlap here between the. You see multiple Gaussians here, one behind the other. May not be of a concern right now because they're all kind of overlapping. Remember which was the column where we saw a perfect match? The central values. What is the column? Bore. Height. Height was the column. This is the distribution of height. So in distribution of height, now look at this. The distance between mean and median was almost very nil. And the tails were also equally spread. We were expecting a normal distribution, but unfortunately it's not normal. What it is showing here is two Gaussians, two normal curves are overlapping each other. Okay. This is what we call the mix of Gaussians. Go to the other columns. Look at this one. This one has a long tail on the right side. A long tail. It also seems to have, but these Gaussians are ignorable. They're very small compared to the other one. Okay. So look at the distributions, and on the distribution part, on each one of the columns, some concern, but not too much to worry about. You should never expect a theoretical symmetrical normal curve in the distributions. All algorithms assume that the data on the independent dimensions are distributed normally. Okay, that's all they assume. Apparently not so, but still it's close to normal, so I'm happy with it.
Can you explain the compression ratio, that one?
This one?
No,
this one? Okay.
Compression ratio you see here, this is compression ratio. And compression ratio, what I'm seeing here is, there are two different clusters in it. Two buckets in the data on that particular dimension. Okay. This is a clear indication of mix-up of Gaussians. When you build models, especially linear models, you should not mix Gaussians. Every Gaussian has a particular characteristic. What do you mean by Gaussians? Gaussians means distributions. Okay. So if on a particular dimension, you have two different distributions, you are talking about two different processes which have generated this data. Remember, in statistics, you would have done a t-test or a z-normal test. When do we say the two data sets belong to the same process? When they're significantly overlapping each other, the central values are not very far away from each other. If the central values are very far away from each other, likely that the two data sets have not come from the same source. If the two data sets have not come from the same source, how can we include them in one single model? What is a model? Model is predicting the behavior of the source, the process which generated the data. Right? What happens when you use mix-up of Gaussians like this is, you're going to find x bar. X bar is going to lie somewhere in between these two, which neither represents this nor represents this. But your linear model is going to go through the s bar, x bar. So your linear model will neither be good for this prediction nor will be good for this prediction. He has done some typo. Hence, a lot of typos sitting on the extreme end. This happens when you measure these terms in some fractions and he's either added one extra zero or something of that sort he's done, because of which you're seeing outliers cluttered together in one group. So I have to go and find out what are these records which is causing this long tail in this cluster. My hunch and experience tells me this is most likely a typo rather than data coming from two different sources.
Yeah, yes. This will be significantly big.
How will you identify that portion?
Go and put 1.96 standard deviation limit. Yeah, this is outliers. Outliers. So I can detect anything which is lying beyond 1.96 standard deviation on this dimension.
So I can identify this.
But standard deviation will be given for the complete observation, right? But that includes data of the this
Doesn't matter. As long as they're beyond 1.96, they're suspect.
So when you replace those outliers with values, proper values, then your standard deviation will collapse.
I think Selena is the best example for what you are explaining.
I'll look at this. Guys, since this point has come up, I'll discuss this. In your original raw data set, suppose it's distributed beautifully, you have outliers here. You do something about the outliers. You identify the records and replace all these values with the median. Suppose you do that. Okay. When you do that, you remove the outliers, replace all the values with median. Your curve will become sharper. When the curve becomes sharper, standard deviation decreases. When standard deviation decreases, the data points which are earlier not outliers, now they become outliers because your standard deviation is decreased. So 1.96 standard deviation for both sides has decreased. So new data points will come out as outliers which earlier were not identified as outliers. And this will continue to go on infinitely. So just handle the first level of outliers. Forget the second level of outliers. They're not really outliers.
Alright? Yes.
Generally, that -2 standard deviation plus 2, right? You mentioned 1.9.
1.96 because 1.96 covers 95% of the confidence level. Some people use 2 standard deviation. Some people even use 3 standard deviation. That depends on your, where it's a matter of life and death, and I want my model to be perfect as close as possible. That means I want my deviations to be very tight. Where I can tolerate some errors, my deviations can be low. Right? So it depends on your requirement.
Yeah, correct.
Because I'm 2 different clusters which I'm seeing here. But since the size is very small, my hunch is it's the outliers. And the outliers have been introduced through some manual problems.
Alright.
So in this case, it is good to retrieve the outlier, or we can just remove the error. We can remove the record. That's also one strategy.
Removing record is always the last option because you're going to lose so many other column informations when you remove those records. Row only, he's talking row. He's dropping the rows. So if you start dropping the rows for all columns where you have outliers, your data set might shrink.
That we have on in the last exercise. So what happened here, they were having a 30 attributes, breast cancer ones, right? So now every column except one, every column has an outlier. So when we are removing the outlier for every column, 569 records coming down to 237.
So that's not good.
That's not good.
So dropping records is always the last option when you have plenty of data. When data size itself is restricted, dropping records is not a good option. Shall we move on? All of you? Okay, let's move. So now always start by analyzing the diagonals first. How the data is distributed on each column. This is my univariate analysis. This is what the output of DF describe is. How your data is distributed on that particular column. It's a basic statistic. It's a descriptive statistics. Next we do is bivariate analysis. In bivariate analysis, how these columns interact with each other. For example, if you look at this one, this is telling you interaction between the symboling and this one, wheelbase. By the way, in this square matrix, above the diagonal and below the diagonal, it's mirror image. Either you focus below the diagonal or above the diagonal. Okay, so let's take below the diagonal. So I know this first column is symbolic versus wheel-based. What it means is, as the value for symbolic increases, you see that the wheel-based trend is going down. Wheel-based is shrinking as symbolic increases. Okay, but I'm also seeing a lot of noise. For a given value of symbolic, there are multiple values of wheel-base. So between symbolic and wheel-base, there is a negative relationship. There is a negative relationship. Okay. Look at this. This is between symbolic and length of the car. Since length of the car and wheelbase are almost kind of related, you'll see a negative relationship here also, but not as well as in this case. Look at the relationship between symbolic and width is almost circular distribution. No significant correlation between the two. Right? We can continue to do this analysis. Let me just look at this one. This is compression ratio, yeah, and symbolic. For increasing value of symbolic, compression ratio that you find is, in this range for one group of cars, whereas for other group of cars, the symbolic range of symbolic is very small. For this cluster, if the cluster is a real cluster, the range of possible symbolic values is much less than this cluster. That's what is coming out of this analysis. Okay. Now let us look at the other columns. Let's look at this one. Look at this. This is relationship between wheelbase and length. Obviously, as your wheelbase, this is wheelbase, as the wheelbase increases, the length of the car increases. And you're seeing a positive relationship here. The R value will be very close to 7 or 8. So this is the case where you have two dimensions and both the dimensions are interacting with each other. They are not linearly independent. But the algorithm assumes that all dimensions are linearly independent of one another. Okay. So we have ways of handling this. One way of handling this is find out using your domain expertise whether calculating the length of the car is more prone to errors or whether calculating the wheel base is more prone to errors, measurement errors. If calculating the length of the car is more prone to measurement errors, drop the length of the car. Keep the other one. However, if you're not able to take that call, you might want to run a principal component analysis, a mathematical technique, or singular value decomposition, another technique. Okay, using those techniques, we can create synthetic dimension out of this. That synthetic dimension will be a composite of these two, so I'll drop both of them and keep the synthetic dimension. I'll talk about this when we come to PCA, principal component. Right now, I'll ignore this. Okay. So in the data set, what I'm saying is there are distributions amongst columns which have linear relationship. There are distributions amongst columns which are indicating no relationship. This one, these are all no relationship. But this is negative relationship, so on and so forth. It's a mix. Some columns are related, some columns are not related.
Can you just give us the cylinder one?
Cylinder one? Where is cylinder?
Last.
Oh, sorry. Where is the last? Yes. Which one do you want in cylinder?
Just
Cylinder versus cylinder.
Cylinder versus cylinder?
Yeah.
Right.
This one?
Yeah.
Okay. What is the problem here? If you look at the cars with number of cylinders, okay, in your data set, most of the cars have 4 cylinders, 5 cylinders, 6 cylinder, and 8 cylinder. Okay, most of the cars, look at this, have 4 cylinders. By the way, these data points might be sitting on top of one another. So that doesn't mean your data set has only 1, 2, 3, 4, 5, 6 records for 4 cylinders. Don't do that mistake. Your data set might have hundreds of records for 4 cylinders, but they're all sitting on top of each other. So that's why you're seeing only 6 dots.
Most of the data have 4 cylinders. Some of them have 5 cylinders, some of them are 6, some of them have 8. Only few records have 12 cylinders, very few records have 2 cylinders. Now when you go to the extreme end where cylinder versus cylinder, that's why you see a peak in 4, some peak in 5, then you'll 6 and the small peak here. None of the other have any peaks. Now cylinder is a numerical column, integer column. You can have 1 cylinder, 2 cylinder. Then what do you mean by the spread? What is a spread? How can you have a spread on integer columns? This diagram which I plotted here is called KDE, kernel density estimates. So there are 3 words in this. First word is it's an estimate. It's an estimation of the possible distribution, density distribution, density estimate in the population. In the population, how the cars are distributed around this value in cylinder. It is a density estimate based on a mathematical function. That mathematical function is called kernel. So using a mathematical function on the available data, I'm estimating how the density distribution of this column is likely to be in population. That is why you're getting the spread. The spread is not in your data. The spread is the estimate of the distribution density in the population based on the observations in your data set. So for integral columns also you can have spread like this, because what the kernel is telling you is in the population it's likely to be like this.
If you're building the model on this data set, it's like symboling is something that as to not understood what does it mean.
I actually went and studied what symboling is, but unfortunately I forgot. I should have known.
I mean, if I come to know that this is not of a very significant use, shall I not drop this?
You can drop it. Data, see, you can't do model building without domain knowledge. You have to have domain knowledge. We have to go and find out what the symboling stands for.
But in your drop statement, like we are not dropping symboling, so we should, I think.
Why do you think we should?
Because, I mean, it's also categorical value.
So what? Doesn't matter.
If a car coming from Japan versus car coming from US, the miles per gallon is going to be different. So it's a categorical variable. Origin of the car is categorical variable. It has an impact on mileage.
If you see domain kind of
so symbolism drop the uniform growth variance filter now. What you take as a limit for that? There are columns with values. So there are columns which have couple of values and there are some with 3 values, and you decide to drop all of those. So how do you determine which one is picking?
Look at the ratio of the distribution. In a column, there are 8 values, but majority of the records is with value 1, very few percentage of value 2. Then that becomes a low variance filter. That's a candidate for low variance filter. But the skewness in the distribution, suppose I have gender column, male, female. 95% or 90% of the data is males, 5% is females. So I might take a call that this column is going to be useless for my analysis and drop it. So it's a call that you have to take. It may not be 100-0, it might be some distribution, but is that distribution good enough for you to use it? You have to take a call. And that call you will be able to take both based on domain knowledge. If I know the drivers in the people who use the car is 50-50 amongst these gender in the market, I know that. But for some reason the data which I have does not reflect that.
So I might drop the call.
So should we be doing this scatter plot matrix analysis before we drop that? Wouldn't it help that way then do that first and then?
This analysis is done on the original data set. It's not on the dropped data set. You should always, this analysis on car DF, you should always do this pair plot analysis on the original data set, always, okay? Once, because this analysis is what is going to tell you which dimensions are likely to be important, which are not likely to be important. You should always do this on the original data set. Hey, you got your coffee?
Yes, that's right.
But I think here we've already dropped it and we're doing this analysis. This is not on the original.
Hey, no, I changed it here, no? I changed it here. I asked you to...
We've removed fuel type engine indication, all of that we've already removed and then we're doing this analysis.
No, I commented out this line. I just now did that.
But you already dropped the columns, that's my point. You drop first and then you bring this analysis.
Car underscore data?
Yeah.
Oh, you don't have this one.
No, about this. If you go further up, yeah. So you,
Oh, you're talking about these? Yeah. Okay. Yeah. You should be doing this before you do this. Before you do this. Always do your analysis on the raw data set. Okay. All right. Shall we move on?
Just one question.
Yes, please.
We did analysis on compression ratio and the second one is cylinder.
Yeah.
What we found is compression ratio have two Gaussians, so we need to treat the outliers and
Yes.
what are the things.
Yes.
But in this case, we know as per the domain knowledge, we cannot treat the cylinder thing. Right?
Yeah.
Like we cannot change the cylinder 12 to cylinder 4 just because it's kind of an outlier or something like that.
No. What you can do is go back to your data, find out what is a car model, go and refer to the manufacturing because you have all this information, whether this car model can have 12 cylinders. That analysis will do. That is what you have to do. See, missing value replacement, outlier replacement, all these things you cannot do without your any domain knowledge. You have to have domain knowledge. When I went and studied this data set, I found out that for a given car, say Toyota, some particular, within Toyota, one particular subvariant, the data given for mileage was unreliable because the factory manufacturing label itself says the miles per gallon is going to be in this range, whereas this guy is claiming to be so high. So the data itself became a question mark. So you have to do that analysis. Okay. So when you do a real life project, when you get into capstone project, you have to reflect all these things. How did you analyze your columns? How did you handle your outliers? How did you handle your missing values? And you have to justify your strategy, why you did that. You can't blindly replace something with a median. That may not be the optimal strategy.
Right? Shall we move on? Okay. Let's
For symbolic means cars are initially assigned a risk factor symbol.
Risk, yeah, correct. They are assigned a risk factor. Yeah, that risk factor is what they connect with symbolic. Can you just read out more louder?
The cars are initially assigned a risk factor symbol associated with this price. Then if it is more risky, the symbol is adjusted by moving it up the scale.
Okay, all right. So this is a risk factor associated with the car. And this reminds me, the risk factor associated with the car depends on the color of the car. I don't think we have color here. It depends on how the car has been driven, how the car is driven. These days, a lot of people, they take pride in telling that my car has so many chips. If you buy these high-end foreign brands, they all come with embedded chips. Those embedded chips, in real time, they capture the data about your driving style and pass it on to a central server, where they sit down and analyze. And the risk factor is adjusted, recalculated, recalibrated, based on how the car is being driven. The symboling reflects that. Right? Okay, let's move. Now, are you able to understand how to interpret this pair plot? It'll come through experience, but this is where you have to do it. Okay? Move on. So what I'm doing here is, from the car underscore df, I am dropping the price because that's my target. And whatever columns I am left with, I'm capturing that into X. So I'm creating a new data frame called X, which will now have only those columns which are independent variables. The target column price will not be part of X. Then once again, I'm dropping number of cylinders here because this is the same problem. It's a low variance filter again. But if you wish, you can keep it. Then what I'm doing here is, from car underscore df, I'm dropping the price. And sorry, I'm not dropping the price. I'm selecting the price column and storing it in Y variable. So X variable is all columns except price. Y variable is only the price column. So if you have 1000 record 10 columns, this will become 1000 record 9 columns. This will become 1000 records 1 column. Are you all okay with this? So I have segregated the independent and the dependent variable. If this was R, I don't need to do this because R takes in as input only one single data frame. and along with that a formula. Whereas in scikit-learn, I have to separate this data into independent and dependent variables. Then I'm making use of the random function which generates the training set and test set. We call it train test split. When I make use of this train test split on X and Y, I'm asking it to split the data in the ratio of 75-25, 25 for test, 75 for training. The output of this will be four data sets. So let me explain this to you, because some people get confused here. So if this was my data frame df, this was my target variable iv, independent variables, target. First thing which I did is I captured the independent variables and stored them in X. I took the target variable and stored it in Y. Then on this X and Y, I did a train test split. When I do this, what happens is it breaks this X and Y both into X underscore train, X underscore test, Y underscore train, Y underscore test. This training label, Y underscore train, is for this X underscore train. This is my test data, X underscore test corresponding Y underscore test. Now when I build the model, what I will do is I'll call the fit function, fit, and with the fit function I'll supply these two. This one, X underscore train, and Y underscore train. I'll supply these two. This is at this point, the gradient descent will come into play. It'll identify for you the best fit model. The best fit model will reflect the relationship between Y, this one, and X. This X comes from this training set. So it will be of the form Y is equal to M1 X1 plus M2 X2, so on and so forth. How many columns are there? 16. So M16 X16 plus C. This will be the model. Once the model is built, we want to evaluate it. We want to see how it performs. To this model, I'll supply the X underscore test values, which means these values. And it will give me the predicted values, Y pred. Are you getting it? So I supply the test data, the X underscore test, only the test data to this model. The respective columns get multiplied by their coefficients for every record. For every record, I get Y underscore pred. What is the predicted price for this car? In the data set, I know my actual Y underscore test is this. Predicted Y is this. What is the difference between these two? That will be my accuracy. Accuracy will be the difference between the Y underscore test, which is actual test labels, versus Y underscore pred, which is your predicted test labels. Right? So let's see this, but before we go there, yeah, I think we can do it comfortably. So let's look at this. Train test split. I'm calling the linear regression here. This is where I'm instantiating the linear regression model. This is where this class becomes an object. And in that object, there is a function called fit. I'm calling that fit function and supplying the training set. When you run this, this is the point where the best fit line using gradient descent is found for you. Now look at this, I'm printing out the coefficients of all those, the best fit line, the best fit plane, hyperplane rather. So when I print the coefficients, these are the coefficients. Now we need to understand what this is. You said there are 16 columns. So the 16 columns have 16 different coefficients, M1, M2, M16. This is that M1, M2, M16. M1 is 88.57, M2 is 71.82, M3 is minus 93.38. All these are those M1s. So let's understand what it means. What it means is, for every one increase in symboling, 1 unit increase in symboling, the price of the car goes up by 88.57 units, dy by dx. For every 1 unit increase in the wheelbase, the price of the car goes up by 71.82 units. Whatever the units may be, dollars, yen, rupees, whatever it might be. For every 1 unit increase in the length of the car, the price drops by minus 93.3 units. Now look at this. This is where you need to be careful. We know that wheelbase and length are positively related, we saw that. Then how come one has a positive relation, other has a negative relation? But both of them should be positive, no? Wheelbase and length are positively related. But one of them is having a positive impact on the target, the other one is having a negative impact on the target. How can that be? Such things indicate to you something is not right in your data set. And one thing which is not right in your data set here, we all know that, is multicollinearity. Engine size, when engine size increases by 1 unit, the miles per gallon, price goes up by 251.74 units. Okay, that is the way you have to interpret this. But what is happening is, some of these ratios are kind of not gelling in, they're not fitting in properly. For example, we already found the length and the wheelbase, they are going in opposite directions. Okay, that is one problem. Then we have horsepower. When horsepower increases by 1 unit, your car price goes down. Whereas actually when horsepower increases by units, car's price should go up. Horsepower increase means large cars. Large cars, you pay more price. Bit more considered, but this is not only negligible, it's also the wrong direction. Right? Good point. Right? So there are problems in these coefficients which are not falling in line with our domain knowledge.
So this coefficient is what we are talking about, right? So is it saying about the weightage kind of thing? One thing I'm not able to understand is when it say 88, okay, it increased by 88 when unit change, keeping other constant. But some values is talking about 6,000 line, 6,000 scale, one is talking about 88. If we compare among each other, it's a huge difference. So how we are going to interpret this in a
The reason why the 6,000 is happening is probably you have an outlier on that dimension which is pulling it, right? So we have not addressed the outliers here. One reason could be that. The other reason is if you're not able to, I mean, if these numbers are not falling in place, then we can convert them into z-scores. The entire data set can be converted into z-scores, and then we can look at this. But the magnitude of the difference, you will still see that the magnitude is still there. Okay, the difference is still huge. And the root cause of this problem that we are seeing, the root cause for this is, 1, we have not handled outliers. 2, we have some kind of a, correlation between the independent variables, which you noticed. We have not done anything about that. Multicollinearity. Right? So those are the core reasons which you will come across in all data set, which lead to overall model level problems. Okay? Now I'm going to take you through further down into slightly more deeper stuff. Let me see if I can cover it today. If not, we'll start with fresh minds tomorrow, because I need that particular thing needs a lot of brain energy.
Brain power.
So right now, all columns has specific units. They are not normalized. So this coefficient is on the not normalized data.
Correct.
So it's always better to have to normalize the things and then calculate the coefficient. Is it like that? Because otherwise you are not able to relate the coefficient.
The coefficients will not change when you normalize. It doesn't matter. By normalizing, you're just centering the data to 0. The relationship between y and x will remain same, whether it's a normalized data or a non-normalized data. Coefficients will not change. Linear regressions are not impacted by normalizations. The accuracy score, the coefficient, everything remains same. Okay? Shall we move on?
Yes.
So linear regression only gives the coefficient, but not the power of that x square, those things. Like we cannot.
No, this is simple linear model. If you build quadratic model, then it will. Right? So let's move on and let's see the intercept. This is the intercept. I'm printing the intercept. What you need to do is model.intercept. This is the model name. Model name.intercept. This function will give you the intercept. Whereas if you want the coefficients, you have to use model.coefficients. Look at this. For coefficients, it is model.coef underscore. Coef underscore will print the coefficients. Model.intercept will print the intercept. Now the intercept that we are getting is minus 12323. There's an array. In that array, we are passing the index. So the first one is intercept. In the other array, we have the coefficients.
I just tried
coefficient also we are passing 0.
Yeah, that is a different array. So I'm saying starting from 0, I know all the coefficients.
Yeah. In my code, I just tried regression model dot coefficient. So just that much. Yeah. Regression. The dataset dot coefficient.
Dataset.
This I just typed that code. It was showing some other results. It's not showing the whole set of it.
No, are you sure you're getting 0 in the IDX? No, you have to do this. See, this is a different array. In that array, I'm accessing all the elements of the array using this, which is why it's printing out all these things. You have already done that. After fitting it, the output of this is best fit line. The best fit line has coefficients. All the coefficients are internally stored in an array which is accessible through this function. This function is accessing that array and printing out the results. Similarly, there's another array for your intercept. It's accessing that array using intercept. We don't know what that name of the array is. We can only access that array through this function. This point in the graph, all these coefficients in the graph are the lowest point in your error. This is error. There are multiple 16 dimensions over here. This is the lowest point. This combination of coefficients gives the lowest point in the error graph, the best fit. Right? So let us look at the performance of the model on test data. And as you can see, performance on the model on test data is 83.6%. Not bad, not good either.
So what does it mean to 83.68?
The comparison between this and this. Okay, so the 83.6%, what do you think it is? No. This is your coefficient of determination. 83.6% of the total variance in your data, test data, has been captured by your model. R square. This is not adjusted R square, this is R square.
That means 18% we still don't know why.
Yes. Sum of square errors.
X minus mean.
Xi minus x bar is for 2 by n. That residual error is 17%. 17% of the variance in your test data has not been explained. Alright?
So where does the intercept lie on the graph?
intercept is one of these dimensions. Error is a function of slopes and C. Error is a function of M and C, right? So C is one of the dimensions. What I showed you earlier was only one M and C. Here you have 16 M's and 1 C. We can't visualize it, so I'm not able to show it. That's the problem.
This 83.6% prediction is accurate.
It's the coefficient of determinant. How much of the variance in test data has been captured by your model, explained by your model? Shall we move on? Okay. Now we need to improve the performance of the model. Your first cut model will never give you the results that you're expecting, very rare. So you'll always end up in another cycle where your objective will be how do you improve the performance of this model? How do you notch it up? So there are various things you can do, but before you do that, I would like to introduce you to a library called stats model. Stats model, the formula API, SMF, stats model functions. Okay. What happens is, when you build these linear models in R gives you a lot of statistical information about your attributes and your models. Scikit-learn linear regression does not give you those information. But there was a lot of demand for that kind of R kind of analysis in Python. So those people who support Python, scikit-learn, they came out with this library called stats model. Stats model tries to replicate the behavior of R, okay, and gives you a similar kind of statistical analysis as you would have received or obtained in R. So let's see what it does and why is it required. So I'm importing statsmodel.formula.api. I'm importing something called SMF. SMF is a bunch of statistical model functions. And this, I'm going to build a linear model using this. But before I build a linear model using this, I have to combine my X train, Y trains into one data frame, because R takes as input one single data frame. It does not take independent variables, dependent variables separately. So I'm recombining the two into one using concat function. I'm creating a new data frame called cars, which now has both the Y and the independent variables put together for training. Okay. Now look at this. When you do cars head, you get the price column on the first column and the rest of the columns. Now I make use of the SMF.OLS. OLS stands for ordinary least squares. Linear regression, ordinary least square. And as input to this function, I give price a formula where I say price is a function of the various columns. The plus which you see here, this plus is a field separator. It's not a mathematical plus. And at the end of it, you will see the data file name. Sorry, the data file name is cars. There you go, data is cars. So the output of this is once again the same model. But this model has been built in R. R-based, similar to R libraries. So the model is price is equal to, I'll take the intercept later, symboling is 88.57. 88.57 symboling plus 71.82 wheelbase minus, I'll just take one more, 93.38 car length, CL, and so on and so forth. The last thing being minus 123.06 or something, intercept. This is your model. This is the representation of your best fit line. Now you can write a code in Java in Java where you have a function, where function takes as input 16 variables, multiply those variables with the respective coefficients, subtract this intercept from that, and give the output as your predicted price. Convert that Java code into a runnable jar file, productionize it, your model is in production. All right? So that is the model. Same model we got in scikit-learn, same model we're getting here, but here we're getting some extra results, which we did not get in scikit-learn. Do some of these things look familiar to you? R square, adjusted R square, look at the difference between R square and adjusted R square. Adjusted R square will always go down when you add useless columns. R square will always go up. So adjusted R square will usually be less than R square. F statistics, analysis of variance. Remember these words, Fisher statistics, analysis of variance. Then you'll also have AIC, BIC. What is AIC? Hey Guru, we would have covered in stats. AIC is Akai information content, BIC is Bayesian information content. All right, forget it, no problem. Not required. Let's go straight down. Most important of these is your adjusted R square. Adjusted R square is lower than R square. 80%, is it okay with you? You have to decide. But before I go there, I'll come down to this. Okay, I'm going to stop at this point. What is this table telling you? I'll just take one example and you have to use that example on others. Okay. Then I'll tell you why this is not there in Python. Now you take any one of these dimensions, say length. The coefficient for length is minus 93.3. We already seen that. And then it gives you standard error, t values, probability of t values. Remember your hypothesis testing. When do you reject null hypothesis? When do you accept null hypothesis? You remember those concepts? Remember we use a p-value there, right? P-values, that is what is this, okay? Now the thing is, let's take one of these example, length. I told you to find the best fit line, the algorithm will try out various lines, okay? And it will find out the errors for each line for you using gradient descent. And I also told you that the best fit line that it finds out will always go through the X bar, Y bar. Agree? So it would have tried out various lines for you before finding the best fit line. For each line on this particular dimension length, you can take any dimension. For each line on this particular dimension called length, you would have had different slopes. Each line would have had a different slope, different coefficient. So those coefficients would have a distribution of their own. Those different coefficients which it tried out on the length dimension before it found the best fit line, those coefficients would have had different distributions. Of that distribution, the one given to you for best fit line, minus 93.38, maybe this one, minus 93.38, how far away it is from the central value is given by your t-score. This is minus 1.2, whatever it is, t-scores. What is t-score? T-score is a z-score. All of you remember z-scores? Xi minus x bar by standard deviation. How many standard deviations away a data point is from the central value? We use z-score for that. When you use student's t distribution, we call it t-scores. Formula is same. Remember student's t distribution? Okay, the formula is same. So the selected value for coefficient for length, how many standard deviations away it is from the central value for the distribution of coefficients on length, that is given by this. The standard deviation of this distribution, the standard deviation of this, which we call standard error in t distribution, that is given by this. This is the standard deviation. This is how many z-scores away it is, your selected value is from the central is this. You multiply these two. Multiply these two, please. Multiply these two. And tell me what is the value you get. Into minus 1.24. 73. You will get back the same value. You will get back this value. Okay? Look at this. If I am doing z-score, okay, z-score centralizes your data, converts the x bar and y bar into zeros. I take any value xi minus x bar by standard deviation is my z-score. Agreed? X bar is 0 because it centers the data. So that means z-score is nothing but xi by standard deviation. So xi is nothing but z-score into standard deviation. Here we call it t, and we call this standard error. So when I multiply t with standard error, it gives me back the value that you had over here, xi. It gives me back the xi. Okay. So that is the way to interpret this. Of all the various coefficients tried out on this length dimension, just select you this one, how far away it is from the central value. If it is too far, maybe it's not reliable. I'll do that analysis using this. The most important analysis which I want to take you to is the p-value. What does this p-value tell you? What the p-value is telling you is, I'm going to talk only for length, but the same thing applies for all. What this p-value is telling you is, probability is 0.2. What is the cutoff probability for your confidence level? 95%? 0.05, 5%. 0.2 is much higher than 0.05. What this is telling you is, even if in the population there is no relationship between the length and the price of the car, no relationship between length and price of the car, null hypothesis, and you're taken data from that population, you're likely to find this kind of a relationship between length and price in your data, which means this is a fluke relation. I repeat, what this p-value is telling me is, probability of finding this kind of a relationship between length and price in your data, even if there is no relationship in the population. In population, the slope is 0 between these two. And from there, you're taken a sample, random sample. The probability of finding this kind of relationship is very high, which means this relationship is fluke. It's a statistical fluke. It's not reliable. Look at this one, p-value. Look at this one, stroke. P-value is almost 0. What it means is, if in the real world, there is no relationship in bore and the price, and then from that population you have taken this sample, finding this kind of a relationship between bore and price, the probability is very low. Probability is very low. I'm talking stroke, sorry. Probability is very low, which means this relationship is not fluke. It is likely to be there in the real world. Okay. So let me put this pictorially and explain this to you. Then we'll wind up. Let's take one of these columns, stroke and price. Same thing applies to all. If suppose between stroke and price, if suppose there is no relationship between these two, then how will the scatter of the data points look? Agreed? All of you? R value will be very close to 0. The scatter of the data points will be circular. Okay. Now, what you will observe is most of the data points are near x bar, y bar. As you move away, the density falls. That is why you get a plot like this on this and a plot like this on this. Are you all okay? When I convert this into 3 dimension, where in the 3rd dimension, this is my x bar, y bar. If I plot the density on the y-axis, question to you is, how will the distribution look? Parabola? cylinder. Keep in mind, very close, it's very high. As you move away, the density falls. So this will be your normal curve, a three-dimensional normal curve. A three-dimensional normal curve is the shape of the density of distribution between two dimensions which don't correlate. This is the shape of null hypothesis. Null hypothesis says in your universe, the data is distributed like this. Agreed? We don't know what the universe looks like, but null hypothesis says it looks like this. If so, and from there I have taken a sample, and in the sample I am finding the distribution between this core, whatever it is, say core, and price, I am finding the distribution like this, where this is x bar, y bar. I am finding a squashed bell curve. I'm not finding a symmetry bell curve, I'm finding a squashed bell curve. This relationship is what is expressed as this coefficient. Now the question is, what is the probability of finding this kind of a distribution in your data if the real data is like this? That probability is expressed as p-value. If the p-value is very low, less than 0.05, that means your universe is not like this. We reject the null hypothesis. Whereas if p-value is greater than 0.5, we say that there is not sufficient evidence to reject the null hypothesis. So I'm unable to reject the null hypothesis. May not be, I don't know, but I don't have sufficient evidence to claim that there is a correlation.
Shouldn't the null hypothesis be, I mean, by default, we are trying to prove the other way, right? So
no, we are trying to establish whether null hypothesis is likely to be true or not. We can't do the other way. We can't prove alternate hypothesis is true or not. We can't do that.
So shouldn't the null hypothesis be, there's a relationship already and...
No, null hypothesis is no relationship. They are independent. It always negates your alternate. Alternate says there is a relationship. Null hypothesis is nothing doing, there's no relationship. No relationship means this is the way. Now the question is, from this you have drawn the sample, in the sample you are saying this, what is the probability of seeing this kind of a distribution if it's coming from this? If the p-value is less than 0.05, we reject the null hypothesis. If p-value is 0.05 or greater than or equal to, we say we don't have sufficient evidence to reject the null hypothesis. So we accept the null hypothesis likely to be true, we reject this. This analysis R provides, Python doesn't. And if you look at this, this is the p-values. So this tells you the importance of the attributes. Those attributes whose p-values is greater than 0.05, useless. Statistical fluke. Those attributes where p-values is less than 0.05, good attributes. Let me be a killjoy, okay? In the statistics community in the real world, there is a vertical split between the statisticians. One school of thought says p-values is not reliable. The other school of thought, which comes from the conventional statistics point of view, they say p-value is reliable. The reason why they say p-value is not reliable is you can go and check it yourselves. Suppose I drop one of these dimensions with high p-value, symboling, and redo this analysis. All the other p-values will change. Now the question is, between your price and your length, if there is a relationship given by the coefficient, why should that coefficient change when I include another dimension, width? Why should it change? It should not change, right? The relationship should remain relationship. Why should the intensity of the relationship change when I add another dimension to it? But when you actually go and analyze this, drop the dimensions, you see that all coefficients change. Correspondingly, all the p-values will also change. The reason why they change is collinearity. They are not truly independent. Since there is collinearity and they impact each other, the coefficients are not reliable, hence the p-values are not reliable. It is because of this reason, this split between the statistics community on whether they should rely on this or not, scikit-learn guys said, forget it, we don't need this. We have other ways of establishing the reliability of the dimensions and the models. Let's use that. That is why scikit-learn does not give you this facility. But then subsequently under pressure, they came out with stats model libraries, which gives you this. Okay. Now, just to end up the show, what is telling you is p-value, and what it is telling you the 95% confidence within which these values lie. Okay. So if you guys remember 95% confidence level, area of rejection, area of, you'll see all, you'll be able to connect to those using this. I'm going to jump this, I'm going to move forward. Last one, overall probability value of the model itself. Can such a relationship between the price and the other good attributes, does such a relationship exist? P-value is very low, which means null hypothesis overall is rejected. Model level p-value is very low. So after removing all the unwanted dimensions, hopefully you will have a reliable model.
All right.
So do we need to reject or not based on p-value?
The p-value is very less here, so we should
lot of columns.
If you're working for people who believe in statistics and all, I mean, not that I don't believe in statistics, those people expect p-values from you, then you have to use stats model. If they don't care about p-values, don't come here. There are other ways of deciding whether a dimension is reliable or not. Ensemble techniques and all these techniques are available with us. So we use that technique.
Most influencing factor for the price. Then
Use decision tree regressor.
That will list out for you the dimension, as you will see now after lunch. It will list out for you dimensions in terms of importance. Which dimensions are more important?
But don't they again use the p-values?
They use Bayesian statistics. They don't use p-values. You remember naive, you won't have done naive. You remember Bayesian distributions? They use that for this. Some statisticians say that Bayesian distributions are more reliable than this. The name logistic regression is slightly a misnomer. It is used for classification. It cannot be used for regression, okay? Though the name says regression. But there's a reason why it's called regression, not logistic classifier. The reason is, under the hood, logistic regression uses linear models, linear regression. That's the reason. It's a classification method based on a linear regression. The response variable, that is the target variable, can be binary class, defaulter, non-defaulter, diabetic, non-diabetic, or it can be multi-class classification also. I can use logistic regression for optical character recognition. I can do that. And in my personal experience, I have seen and I have also read some papers about it. When I compare models, often logistic regression comes out on the top. If not exactly on the top, at least top few, top 2 or 3, okay, for classifications. So I'm going to start by showing you binary classification, but this can be used for multi-class classification also. Given your independent variables, what is the class likely to be? That is the objective of this model. I can also use a function available in scikit-learn where instead of defining which class an observation belongs to, a test record belongs to, I can print out what is the probability that this record belongs to this class versus this class. I can even print probabilities. Okay. This particular function is nothing unique to this. It's available in all probability-based models. Predict. You remember we use predict? We just add underscore proba. This function will print out probability values. If you go for just predict, this will print out the classes. Decision tree also has this, naive-based algorithm also has this, logistic also has this. Predict underscore proba. Let's take a hypothetical situation. Don't worry about the PPT. Let's take a situation and discuss this concept. And for that, we are going to use 3 colors. You are a data scientist, you're working in a bank, and you have been tasked with, you have been given a responsibility to build a model where the model will take certain inputs and the output of the model will be, is this person likely to default? If I give him loan, is this person likely to be a defaulter or a non-defaulter? You have to build that model, okay? So what kind of data will you need to build such models?
His salary income, his student or his profession.
So past history in terms of
Civil score.
Civil score, okay, Civil score is an output of a model actually. So let's keep Civil score aside. You'll need his age, gender, income, any past loans he has taken, any property he has, so on and so forth, so many things. Now let's assume that one of the things given to you is his income. Forget it, this is a touchy subject, so let's call it age. Okay, one of the inputs given to you is the age of the people. So you have the past data with you. The bank has given you a past data set. In the data set, you have both defaulters, non-defaulters, and one of the columns in the data set is age. You notice a pattern here. The pattern is most of the defaulters, okay, most, not all, most of the defaulters are in the lower age bracket, okay, and you also notice most of the non-defaulters are concentrated in higher age bracket. But that doesn't mean there are no non-defaulters in low age. Okay, you observe this pattern. Now, since there are two classes here, what we're going to do is we are going to say green class, we're going to assign a numerical value 1, red class, numerical value 0. Remember, we can't work on string data types. So the target columns will be assigned numerical types. Okay. Why 1 to this, why 0 to that? No reason, you can flip it also if you wish. But we assign a value 0 and 1. We don't assign any other value, we assign only 0 and 1. There is a reason for that. Okay. Now, your object, yeah. Now you find that the pattern over here, as income increases, you find more greens. As income decreases, you find more reds. You have done a linear model already. So what you do is, you try to build a linear model here. So you say, let the y-axis be probability of belonging to any one of the classes, let's call it 1. The y-axis is probability of belonging to class 1. You can actually take it as probability of belonging to class 0 also if you like. The two probabilities will be inverse of each other. So you can take any one you like. Alright? So when you build a linear model, the linear model, anybody has a black pen here? Black. No, this pen. Oh, okay. Now you'll notice that as the age increases, if this is a probability, the probability of somebody being belonging to green, the probability increases linearly. Probability increases. I can represent it with linear models. If I had taken this as 0, if this was 0, then this line, how would it look? It will be reverse. That's the difference. So you can use any line. Okay. So I'm taking this as 1 for ease of explanation because you will be able to connect to what we did yesterday. So the line will look something like this. So this line, y equal to y is probability of belonging to blue class, is related to mx, x is this variable, plus c, c is the intercept over here. C may be 0, c may be negative. But the problem with the linear model is, linear models go to infinity, minus, plus. Probabilities have to be within 0 and 1. They can't be below 0 or above 1. So, we can't use a linear model. We use another technique where we transform this line into an S-curve. This S-curve is called a sigmoid. And it is very easy to achieve this. The sigmoid is nothing but 1 by 1 plus E. E is a Euler constant we use in mathematics, minus mx plus c. So this best fit line, the best fit line which is found for you, this best fit line is fed into this transformation, this mathematical formula. The result of this transformation is this curve. Yeah, sigmoid curve, the property is it will reach 0 at infinity, it will reach 1 at infinity. That's exactly the property of a probability distribution. Now let us interpret what this formula is saying. Keep in mind we are building the model, so which means we are in training set. So in training set we already know the labels of every record, right? The algorithm gets both the input variables and the output variable, x and y. So all the labels are already known, and the labels are shown in the color over here. Are you all okay? Shall we proceed? Now, what the models, now that I got sigmoid, I'll remove this line. I'll remove this line. Okay, this is going to infinity. We don't even need this. We don't even need this. Now, what this model is telling you, let's look at that. If you take this red point, look at this. If you take this red point, what the model is saying is the probability of belonging to blue class. What is the probability of this guy? Suppose we don't know the color. What is the probability of this point belonging to blue class? It's very low, which means it belongs to the red class. So the model prediction and actuals are matching here. The model prediction and the actual label, both of them are matching. Take this green one. What the model is saying is, what is the probability that this green point belongs to blue class? This is probability of blue class, right? The probability is very high. And he is actually green. So both prediction and actuals match. Right? Hey, lady, are you with me? Sure, 100%. Okay, don't get left behind. Your expressions tell me a lot of stories. I have conducted more than, I lost count, more than 250 sessions now in data science. So I built a model. You know what's coming, right? So looking at the place, the position people occupy in the class, I can guess a lot of things about the person. Believe me, we all follow patterns, and you'll be surprised. I've noticed this pattern without fail. Based on the position people occupy in the class, okay, of course, latecomers, they don't have a choice, but people who come early, okay, based on the positions they occupy, I can draw a lot of conclusions from there, inferences from there, right? So people who are feeling doubtful but are able to ask, they're not asking, I know I can identify such people. Okay. So feel free to ask, okay? All of you, please feel free to ask. Don't get left behind. I was always a backbencher. I was always a member of the backbench society. I'm not saying anything to you. Don't look at me. If you sit in all places means? I was always a backbencher, so I know more over the backbench than the front bench. But other patterns which I observed was during the sessions, right? So a deviation from our main topic of discussion, bottom line is don't hesitate to ask. Okay, feel free to ask, don't restrict. Coming back to this, are you all with me on these two discussions? Okay, now look at this point. You see a red point here, this one. What the model is saying is, as per his income, he belongs to, probability of he belonging to blue class is very high. So the model will pass him as blue. Sorry, in this case green. Green, in this case green. So what the model surface is telling you is predicting the probability of belonging to the green class. It's very high. So the model will classify him as green, but he is actually red. So model has done an error over here. Mistake. Similarly, If you look at this one, this side, the green point here, can you tell me what the model is telling you? The model is telling you the probability of him belonging to green class is very low, so he's likely to be red. But actually he's green. So the model has done an error here, a mistake. Okay? So whenever you have overlapping data sets, as in this case, in spite of the best fit line, the classification, you will find some errors. There will always be errors. These errors are called training errors. Errors in the training data. Okay? All right, no problem. Which one is -1? This is 0, this is 0, this is 1. And this axis in this particular picture, this axis is probability of belonging to class 1. Okay, that's why your S curve is coming like this. This S curve has been built out of a linear model. If you had taken this, as probability of belonging to class 0, then it would be reverse S curve. Because your curve would be like this, the line would be like that. Oh yeah, all models have problem with outliers.
So can you explain what is the reason you have taken S curve rather than the linear?
Can somebody answer that question? Why S curve?
Because the linear was it will go to plus infinity to minus.
Hey, linear will be overfit. Who said that? What did in linear models, we don't have any boundary. They go to plus infinity, minus infinity. We don't want that. Probabilities have to be between 0 and 1. That's why they will convert into sigmoid. Sigmoid curve has that property that will always remain between 0 and 1. So we are able to map the numerical values to probability function.
So coming back to the same question, now you explained the binary thing. So same thing is applicable for the multi-class.
Yes, in multi-class classification, it will be 1 versus rest. Suppose I used this logistic regression for OCR, optical character recognition. So you'll have one S curve for A versus others, one S curve for B versus others, so on and so forth. So in your mathematical space, you'll have multiple S curves cutting each other. One is for A versus others, the other one is B versus others, C versus others, so on and so forth. All these algorithms, decision tree, naive Bayes, support vector machines, neural networks, logistic, they all break your mathematical space into compartments. They break them into compartments, pockets, where one pocket belongs to this object, the other pocket belongs to that object. All of them do that. You done decision tree yesterday? Which data set did you use? Diabetes data, PMA diabetes data set, okay? That is a binary classification actually. So when you make decision trees, okay, this is the structure you have of decision trees. What you're doing here is, this entire mathematical space is your root node. The entire data set, all data points put together is your root node. Then you find out one particular column on which you break the data into two. That is like putting a vertical boundary here. So these two now are these child nodes. But you have not achieved your what you call homogeneity. Your Gini index is still very high, or entropy is very high. It's still not pure leaf. So what you do is you again find a column here in this data set and break this into two. That means you're drawing a vertical boundary. So this and this is the child node here and here. So decision tree also breaks your mathematical space into pockets such that each pocket becomes homogeneous at leaf level. So right now I've reached the leaf level. Hopefully at leaf level, each pocket is become homogeneous. Now I know what are the conditions under which somebody belongs to this pocket. That is called the rules of the decision tree. All algorithms break your mathematical space into pockets, including logistic regression.
For this
You treat A as class 1.
For this family, the default is
This is binary class classification. If you're in multi-class classification, optical character recognition, then you treat at one point in time all data belonging to class A, alphabet A as 1, and rest of them are zeros. See what is the boundary. Then treat all the records belonging to class B as 1 and rest of them zeros. Then redraw the boundary. So you'll have multiple boundaries cutting each other.
Which is like multiple variables affecting a particular attribute that we're trying to tell. For example, if a customer is fraud or not, if I'm considering age as a factor, I'm also considering gender as a factor, I'm also considering...
That will be hypersurface. Hypersurface. But multiple hypersurfaces for A, for B, for C. You'll have that, right?
So will that be consolidated single mathematical space?
Yes, 100%. Yes. The whole model will be a composite of all these surfaces. Okay. Let's move on.
So multi-class is always 1 versus A, rest.
Multi-class classification, most of the algorithms give you OVR. OVR means 1 versus rest. Some algorithms give you a facility of replacing the OVR with Bayesian probabilities. Okay, you can actually go and modify that in your hyperparameters. But most of the algorithm by default will give you OVR. Right? Some algorithms like support vector machines, OVR is not very efficient, so they give you another technique called Bayesian probability based. Shall move on? Okay. It has a gradient descent algorithm working under the hood to find you the best fit line. Right? The linear model uses gradient descent algorithm. Do you remember gradient descent discussion we had yesterday? See, the gradient descent is to find best fit line. I'll quickly summarize this. I know it was too much in one day to cover. Your error function will always have this form, not very difficult, guys. If I give you equation y equal to x square, for any value of x, y will always be positive. It's a squared term. If x is -1, -1 into -1 becomes +1. This is called a convex function. So whenever you have any function raised to power 2, it will always be convex. Right now this is single dimension. This x can be multiple dimensions. So if I take 2 dimensions m and c and plot the error, this will be a bowl shape. Right? Now in this ball shape, we have to reach the global minima. It's guaranteed you will have only one global minima. You won't have any other. For quadratic error expressions, you will always have one global minima guaranteed. Okay. So we start with some random MNC. That random MNC gives us some error. The same concept applies in logistic because logistic is also a linear model. Right? From that MNC, it will come down to this using your partial derivatives. Concept, okay? There's a lot to discuss in this. I'm not going to discuss all those things at this point, but you will need this if you're going to do deep learning, neural networks and all those things. Right? At that time, we'll take it up in detail. Same concept will apply today in logistic because logistic uses linear model under the hood. So it finds for you the best fit line given the spread of the data points in mathematical space or best fit plane or a hyperplane. Once that plane is found, that plane is sent through the sigmoid transformation and it's converted to S curve. Right? Now the driving force behind this, here in this case it was quadratic. In this case, the S curve which is formed, the S curve can be shifted forward, backward, upward, downwards. Let me see if I can show this to you, okay? What happens is, insert, if I take this S curve, I hope it works. Yeah, it works, okay? Now this S curve, you can move it up by changing the C in y equal to mx plus c, or you can move it down. You can flatten it. To flatten it, what do you think we'll use? The slope, m of the line. By changing the slope, I can make it vertical or flatten or move it up and down using C. So by using these two parameters, m and c, I will find out which sigmoid surface I get is the best surface. And to find out which is the best sigmoid surface of all the infinite possibilities, it uses a function. That function is called log loss. This is just like your gradient descent. Okay? Don't worry about this function. It's actually very easy. Looks dangerous, but actually it's very easy. Now let us look at the log loss function. Looks very dangerous, but it's actually simple, very simple. Okay? So forget the sigma and all these things. Just take the expression yi into log of pi, okay, plus then 1 minus yi into log of 1 minus yi into log of 1 minus pi. Correct? Just look at this expression. What is this y? Y is the target variable. Target variable. We know the target variable ranges from 0 and 1 only. 1 is for green and 0 is for red. So this yi can take a value of 0 or 1. Okay? Now let us look at 4 situations. I'm going to show you 4 cases, and the 4 cases we're going to discuss here. Where is the 4 cases? These are the 4 cases. Look at the first case. In your data, the first test case, these are 4 test records. Okay, the first test record has this income. The model is saying the probability belongs to blue class is very high and is actually blue class. No error, 0 error, right? 0 error. Come to this. What is the y value for blue class? 1 into what is the probability? Very high, almost close to 1. Log of a very high number, when log comes close to 1, this is 0. Log of a very high number is 0, close to 0. 2 raised to power 0 is 1. So this is log to the base 2. Okay? So log to the base 2 of a very high number means close to 1, will always be 0. Come to this term. This becomes 1 minus 1. We don't even need to evaluate because this is 0. So when you do correct classification for the blue points, your error is 0. Let's take the next case. The next case is this red point. Let's take this red point. Let's take the case number 3. Or let's take case number 2, the second case. Okay? As per the model, given his income, the probability of him belonging to blue class is very low. Which means the model is predicting that he belongs to the red class. As per the income group of this person, the model is a blue line. It's saying probability of him belonging to blue class is very low. Anything below 0.5 is very low. So the model is predicting that this guy is going to be red, but actually he is blue. So let's see what the equation says. He is blue, value is 1. Probability is very low that he belongs to blue class. The model is saying probability is very low. Log of a very small number is a very large number. So this is into a large number. Okay? Since he is a blue class, this expression we don't even need to evaluate. It will be 0. So whenever you do misclassification of the blue, you get a very large error. All right? So the more the blue class is on this side, larger the error will become. So in technical parlance, what we say is, more confident this algorithm is about a particular classification, which we know is wrong, more the error it does. Right?
So if the probability is less, because in this PI would be, if it goes lesser, then the larger it becomes more large.
Yeah, correct.
The error will go more. If you go down, it will still further.
So for this blue point, where the probability of him belonging to blue class is almost 0, this error will be very high.
So what we are saying is more error we do on this side.
For blue class.
For blue class, then loss is more.
Yeah, exactly.
And upper side, even the error is there, but loss is less.
We'll come to that. We'll first discuss only the blue class. The more blue points are on this side, in this case, the more the errors will come out. Larger the error will be. Okay? Now look at this, the red one, the fourth one. Or let's take the third one, third one. We know that this guy is a defaulter. The class is red. The model is given the income, the model is predicting he's going to be defaulter. Come to this equation. What is the label value for this guy? Class red, 0. So this expression becomes 0. We don't even need to evaluate. Come to this guy. 1 minus 0 is 1 into log of a very small number. Number minus 1 becomes almost 1. So this expression turns out to be 0. Log of a very large number, okay, is 0. So this expression comes too close to 0. For red classification, we use this part of the equation. For blue classification, we use this part of the equation. Take the last case where the red class is misclassified. The model is saying he belongs to blue class.
So one question. So CI is the probability, right?
Of belonging to blue class.
Belonging to blue class. That's why it is 0.
Yeah. See, the model, the surface is probability of belonging to blue class.
Okay. That's why it is 0.
Yeah, exactly.
For the right.
Exactly. Look at the last case. Last case is the fourth case, where the fourth case is misclassification of red. So when you do misclassification of red, this expression is not for red, so forget it. Come to this. This is 1 minus 0 into log to the base 2. This is a very high probability which your model is predicting. So this becomes a very small number. Log of a small number is a very large number. So error is very large. That's all this equation is. So you sum up the errors done across all the data points, those which are correctly classified, those which are not correctly classified, sum it up, you will get the total error across the entire model. Sum of squared errors, same way this. So the objective is to minimize the sum of squared errors by finding the right logistic surface given the classes.
And so the gradient distribution will say that. So suppose it's a high loss, and it will go in a direction where it want to reduce that loss.
Reduce the total loss. Correct. Yesterday, the sum of squared errors was driving the gradient descent. Here, this will drive the gradient descent.
So it does gradient descent first to get the linear equation and then does the second to get the right
sigmoid curve. Both happen together actually, both happen together. It's not one after the other, both happen together simultaneously.
What is the range for this loss? Between the data?
0 and 1. All 100% is your complete loss. Which will happen when you have all the red 7 classified as blue and all the blue 7 classified as red.
Logic sheet always plays with 0.
Yeah, for classification, always 0. All right, shall we move on? Extension of linear model that we saw yesterday. The beauty of logistic regression is it makes no assumption about the distribution of classes in the feature space. Many of these algorithms, linear model especially, if you're building linear classifiers or linear regression, they expect Gaussian distributions. You understand the term Gaussian distribution, all of you? No? Okay. When you build any model, expectation is if you take this attribute, the data will be spread around the central value of this attribute with some standard deviations. Same way, this attribute will have a distribution with standard deviations. When you plot this together in the mathematical space, they will look like, if they are independent of each other, they will look like this. We already discussed this. This kind of a distribution is called Gaussian. So in 3D, it looks like a bell curve. All right. This algorithm does not make any such assumptions, but keep in mind, if you have outliers in your data set, even this algorithm will fall on its face because it is based on linear model. So those outliers have to be addressed. What will happen if you have outliers? If you have outliers, you're likely to have outliers for, say, for example, what do you call them? The class 1. If you have an extreme outlier here, then you're in trouble. If you have outlier on this side, no problem. If you have outlier on this side, you have a problem. So more extreme it is, more severe the outliers is, more the errors will be. Right? Okay. You can do multi-class classification using either binomial distribution in this case or multinomial distribution also is possible. You can also print out the probability values if you're not interested in the class, but I want the probability values. What is the probability it belongs to this class or that class? Quick to learn because it's based on linear model, and you have gradient descent to help us out to find the best fit line quickly. Fast in your test data also. In test data also it's very fast. And as I said, many times I have personally seen logistic regression stands out among the top few in many of the situations. Resistant to overfitting, because as a simple linear model, linear models cannot be very complex shapes. It is resistant to overfitting. Okay. Resistant to overfitting does not mean resistant to bias errors. It means resistant to variance errors, right? But we have another one to deal with. And you can print out the coefficients, the probability values, and interpret the probability values. So the model is not a black box, right? Disadvantage in classifications is it uses linear boundaries. What it means is, if the distribution of the classes is something like this, then the model will suffer. Right now we took a linearly separable this thing, but what if the distribution is not linearly separable? Then logistic regression will suffer. If the distribution was like this with overlap, but it was like this, then it will do well. But if the distribution like this on the attribute you have decided, you see the difference? The difference is, if I plot the density graph, okay, in this case, the two density curves are overlapping. Your t-test, analysis of variance, and all these things will tell you that this record belongs to this class, that class, 50-50. It will not be able to classify. On the other hand, if I look at this situation, your overlap is there, but the central values are shifted apart. So when we have distributions which are linearly separable, may not be 100%, then logistic will do well. But you have distributions like this. I don't know whether you noticed, PIMA dataset is like this. That is why in PIMA dataset, you will not be able to get accuracy beyond 70%, 76%. Do whatever you can, right? So, it will not give you beyond 75. When the data distribution is like this, none of the algorithms will be able to help you out.
When we start building this model, we need to check what our data distribution is like.
100% you have to know your data before you start building the models. You have to know your data, which means you have to know every attribute, how the data is distributed, if you're in classification, how the classes are distributed, which dimensions or which attributes are able to linearly separate the two classes. Use only those for your classification models. You have some attribute where both the classes are significantly overlapping, including the central values. Using such attributes for building model is useless, and PIMA Indians, you will see all the dimensions are like that.
So then what we can do actually? We can't do anything. No other algorithm.
No algorithm. Okay. What human brain cannot do, an algorithm cannot do. So you have to have at least one attribute, as you will notice in another data set that is called bank.csv. There also the data overlaps on all the dimensions between the two classes, but there are few dimensions, 2 or 3, where the data central values are separated apart. Based on this 3, it gives you 96% accuracy.
So for our model, we should consider only those.
Only those, yeah, correct. You don't need to include all of it.
What is the name of that bank.csv, that two attributes? What in the data
Some
set?
attributes, some, I'm just randomly picking.
What is that term called? Gross error?
This is scatter plot. This is scatter plot. Now you find out how the density of the plot changes when you move from this direction to this direction. You will see that the density is very low, very low, very low, increases very high, highest, then it starts falling. So when you convert this into 3D, it becomes a normal distribution. In 3D, this becomes a normal. That is called density function, 3D.
So can we switch the axis for analysis in this case?
Can we?
Can't we switch the axis for analysis?
Switch means?
Say y-axis becomes x-axis so that you are distributing.
What you're basically saying is, no, I'm comparing these two with this over here. This axis is not there. I'm just saying, if you have a distribution like this, your logistic will do well. If you have a distribution like this, your logistic will suffer. Any algorithm will suffer. Okay? But what you're saying is, can't we switch to this axis where the two classes are separated out? That's what you should be doing. So if you have two axes, two attributes, on one attribute they are not linearly separable at all, but on the other attribute they are linearly separable, use the other one. That's what I'm saying. Yeah, all right.
In two-dimensional see like this, we can change to 3 dimensional. We can see some of the data are up.
So use that dimension, which is helping you to separate out the two. Don't use this dimension.
Can we apply one model on one attribute as a other attribute?
That is what random forest does. Random forest, every node of the forest is constructed using randomly selected features from the data set. Yeah, it internally does that. But random forest is the only one which comes close to what you're asking. No, it doesn't do that. It randomly picks up. It doesn't see whether these are the best attributes. All right. Okay, let's move. Let's do a hands-on. This is the same data set. Pima and diabetes data set. Same data set. Shall we do a hands-on on this? Okay. All right, guys, are you all ready? Okay. So if you have access to the code, the first line is matplotlib. We already know what it means. I'm importing from scikit-learn linear model, logistic regression. Yesterday we had imported linear regression. Okay. Then I'm importing matplot, SPLT, Seaborn. I use Seaborn libraries for my plots. Especially pair plot comes out very well in this. So I'm going to use this. Train test split, you already know what it is. Numerical Python. And to measure the accuracy of the model, I'm going to use metrics. So whenever you're doing classification, one of the most important tools for evaluating a model is your confusion matrix. Okay. So that comes through this metrics library. We'll see all those things down the line. Earlier, this Pima diabetes used to be available in UCI dataset, but now I think it has been removed or archived. So it's not available, but I downloaded it from kaggle.com, another site. I'm loading the dataset over here. It's a data file, it's a text file. While loading the data file, I'm feeding the column names here, which I got from the original source, the column names. So the column names are, the first column name is pregnancy, how many times, by the way, this particular test was done amongst Pima tribes, a tribe in South America, where apparently the ladies are prone to type 2 diabetes very early in age. So this research was done by this university where the objective was, can we build a model and predict who is going to have type 2 diabetes by the teenage? Okay, for that they did research on that community. Some of them were diabetic, some of them were not diabetic, and the characteristics that were captured are these. The first one is number of times pregnancy reported by the subject. The next one is plasma level in your body. Plasma is a component of the blood. Then we have blood pressure. This is diastolic blood pressure. This one is diastolic blood pressure. Then we have skin, where apparently people suffering from type 2 diabetes in that tribe, they have some kind of skin folds. This is measurement of that. Then they do some testing. This is called fasting sugar test or something. That is this test. Body mass index. PEDI is another test. Some pedigree test they do, I think. It's another test related to blood sugar. Age. And the last one is your target column, whether this person was diabetic or non-diabetic. Diabetic means 1, non-diabetic is 0. Now the whole thing, that the objective is, we are trying to find out, is there a relationship between the independent variables and the target variable? What is that relationship we are trying to find out? That relationship we assume exists in the universe, in the real world. We are trying to find out whether we can discover that relationship. So for that, we are building this model. And I always do this based on the experience on car MPG dataset. When you look for this head, okay, when you look for some sample records, you see all numerical values. But what is a guarantee that there is no record further down which has some non-numerical values sitting in the numerical columns? What is the guarantee? How do you identify that? To identify that, we can use this method. What I'm doing is, I'm using a numerical Python function, isReal. This function is a binary function. It's a Boolean function. It will give true or false. This function, I'm applying it onto, look at this apply. I'm applying it onto all the rows, all the columns of this. This is the beauty of Python, where you have to do minimal coding. If you had to do this in Java, you'll probably write a for next within a for next over here. So all that thing is taken care of. So what's happening is, I'm going to apply this function isReal on all the rows, all the columns of PMADF. Okay, and you see this tilde over here. This is a not operation. I want only those records where it returns a false. Okay, fortunately there are no records where it returns a false, which means all records, all columns are numericals. What is the other way of finding out whether any such non-numerical characters have come into the data?
Data types.
Df types, that's it. Df types, when you do, it will return the data types of all the columns. If there is any non-numerical value in any of these columns, it will return it as object. That is easier than this, Df types.
So what we do if there is a non-numerical?
What we do if there is a, we have to go and identify the record, convert that into NA, NaN, numerical. Then you can replace with median, mean, whatever replacement strategy. We don't have any such case right now, okay? But we have nothing to be happy about because we're seeing a lot of zeros. And zeros in blood pressure is surprising. It can't be, not possible. Zero in plasma is not possible. But you have zero values in blood pressure, you have zero values in plasma. So missing values are there. The missing values will cause problems. We need to address the missing values. Okay, let's move on. Do a describe how the data is distributed on the various dimensions. Univariate analysis. If you don't like this, don't do it. Do the pair plot. Pair plot also gives you visually the same univariate analysis. Okay. So I'll quickly tell you one. Look at the difference between, for the test data, the test attribute, look at the difference between the mean, 80, almost 80, and the median, 30. The mean is drastically shifted away from the median on the higher side, which means there is going to be some long tails on the right side, on the higher side. Mean gets easily impacted by outliers. So some outlier is pulling mean towards the right side. How do you confirm that? Look at the distance between the third quartile and this. Look at this. Correct. Look at, you're like me, you don't want to calculate? Can you tell me how long is long? The right side tail, look at the length and compare that to the left side tail. Left side, there is no tail. 719 units. So is this possible or is this a typo? We need to go and check. Maybe this is a typo. We don't know. Okay, right, I'm going to move on. The next thing that you have to do is first understand how the data is distributed on your various dimensions. If you think there are outliers, we need to address outliers. We already know we have missing values, we need to address missing values. The next thing you need to do is, since you're in classification, how many records are available for each class in the data set? Look at that. The number of cases for non-diabetic, 0, is 500, whereas the number of cases for diabetic is half of that, almost half. You're preparing for your board exams, and most of the questions that you solve, practice on, is calculus. A small part you do it on trigonometry. Obviously, you're going to flunk in trigonometry, right? Why? Because the pattern of questions that come to you in the exams in trigonometry may not have been reflected by the patterns that you have used. Which means you have not gone through all the possible patterns in the trigonometry questions. Same thing will happen here. To the model, I have given only 268 of the diabetic cases. Maybe this 268 does not reflect all possible permutations that lead to diabetes. So the model will perform poorly in predicting the diabetic cases. It will perform relatively well in predicting the non-diabetic cases, but I want the reverse. The objective is the reverse. Okay? And keep in mind, whenever you're in classification and the classes are skewed like this, all algorithms are biased towards the higher represented class. All models, the objective is to minimize the overall misclassification. So their focus will be on the higher class. So this is another source of bias which comes into the model where the algorithms themselves are biased. So how do you handle this? Make 502? Yeah. We call this strategy upsampling, downsampling. Okay, there is a strategy called upsampling, downsampling, which I'll refer to, which I'll take you through when we do FMT, model tuning, but right now we're not going to do that. There is a package available, it's called InBlearn, but right now we're going to live with this. There's another way of improving the the classification, performing better in the underrepresented class, that is called modifying thresholds. Thresholds. In logistic regression, naive-based, any other probability-based model, the cutoff is 50%. If the probability of belonging to blue class is 51%, the data point will be classified as blue. If the probability of belonging to the blue class is 49%, the data point will be classified as red. So the boundary is at 50%. Okay, I can modify the boundary. Though none of the algorithms allow me to modify the boundary directly, I can build wrapper class around the algorithms. I build the model. Around the model, I write my own class where I modify the threshold. Okay. Once again, I'll cover this in FMT, not now. It'll be too much. So we can play around with the threshold, modify the thresholds to improve the accuracy of the underrepresented class. We can do that. Okay. How do we do that? We'll take it later. But whenever you see in classification skewed distributions like this, be ready. There's no way you can achieve a very high accuracy for the underrepresented class unless you play around with these two techniques. Let's move on. So this is my pair plot. Okay, I don't like this. So let me quickly redo this. All right, I'm going to come into, I'm not going to do all this, I'm going to come straight to this, where I'm going to say SNS pair plot, comma, dag underscore kind is equal to KDE, kernel density estimate. Since these are numerical values, it makes sense to have this. And hue means color, is equal to the last one, what we call it, target class. So hue is equal to class.
So you haven't treated outliers or
Not yet.
the zero values. So you just
Yeah, on the raw data. It'll take some time. It's fast actually. Yeah, there you go. Now let us understand this pair plot. All of you have it? Let's look at the very first dimension. The first dimension here is pregnancy reported. Okay. The blue is non-diabetic class, and the red one is the diabetic class. The orange is the diabetic class. Okay. If you look at it, the two distributions are overlapping with the central values. They are overlapping. Very small separation over here. Come to the next dimension. The next dimension is your plasma. Plasma, you see long tails on the left side with a small bump. This is their outliers, the zero values. But otherwise, both the classes, the blue class is perfectly, looks like almost like your normal curve. And the central values are overlapping. The central values are eclipsed. So once again, not a very good attribute, but at least we have some differentiator here. Look at this one. Even the outliers are overlapping. This is your blood pressure. These are the zero blood pressure cases. They are also overlapping. Yeah. So there is no way your blood pressure will be able to separate out. Based on blood pressure, you cannot distinguish diabetic versus non-diabetic. There's no way you can.
No, but if you correct those zero values,
still, whatever technique you apply will be same technique. So both of them will shift together, right? So we have a problem there. Look at the next one. This is even more surprising. Almost gone. Skin color, not skin color. This is skin fold. Yeah, you see the same problem here also. Every dimension you look at it, every dimension has this problem. On none of the dimensions, except for a few dimensions where you see small difference in the two classes, none of the dimensions are separating the two classes out. So even you put all these dimensions together and build a model, we are not going to have anything. Yeah, it's overlap, almost this case, the previous case, this one. And that's what we are seeing here. The two classes are overlapping on every time. They are not shifted like this. Let's go ahead and build a model. Let's not be very hopeful about this. Any model will give a problem here. So what I'm doing here is, this is not required. It's not required to be done. All algorithms can take as input the data frame itself. But earlier I used to do this as a practice, where I'm converting the data frame into an array. So data frame minus the column headers is called an array. Okay. And that array, I'm taking the independent attributes into X and dependent attribute in Y. And then I'm splitting this X and Y into train set, test set. Is this part okay with you people? All of you with me on this? All of you, Sairam? You're also on this? Great. Now look at this. I'm instantiating the logistic regression model. You can call it anything you like. I'm calling it model. I'm doing the fit. This is where the best fit line is found and convert into your sigmoid curve. the fit. Once the model has been found, then I make use of the predict function of that object on test. So these are my predicted labels, diabetic, non-diabetic. The actual labels are Y test. Okay. Some people get confused here, so I'm going to stop it. Don't look beyond this. Just stop here. I'm asking you to just look at this part. Till this point, everything is fine? Okay. Now what I can do down is, I can, for the time being, I'll remove this, okay? I'll put a, yeah. For the time being, just ignore this. Control X. We'll put it over here. Insert cell below, and we'll put it here. All right. I'll uncommit it later. I'll do that. Okay. Now look at this. Have you seen confusion matrix before? Yeah. All of you agree it's exactly what it's called? It confuses people a lot, right? Confusion matrix. So what I do is, as a practice, when I make my confusion matrix, I always keep the actuals on this side. Actual diabetic, non-diabetic. And the predicted, the output of the model on this side. Diabetic, non-diabetic. This is my practice. You can follow the other way. But whichever way you follow only one. How do you control this? Since again Y test first, this is actual, it goes to the rows. Y predict next, this is your predicted values, goes into the columns. If you flip this, you'll flip that. Now what it's saying is, of the 147 diabetic cases in your, sorry, this is non-diabetic, not diabetic, this is ND, non-diabetic, this is diabetic, ND, D. Awfully sorry. If you go and read the source of the data, they're very clearly told 0 is non-diabetic, 1 is diabetic. Of the 147 non-diabetic in your test data, 132 have been classified as non-diabetic. No mistakes. For this class, true positives. Of the 147, 15 have been identified as diabetic. Incorrect classification. These are those values of red lying on the extreme end, values of blue lying on the extreme end. Look at the diabetic class. 84. There are 84 diabetic cases in your test data. Of this 84, 46 have been correctly classified as diabetic. 84 minus 46 is 38. 38 have been misclassified. Okay? Now look at this. Now look at this. What is the overall accuracy? 77%. Looks decent. But let's look at accuracy in diabetic class. Okay? We call it recall. Recall is, the formula for recall is true positives by true positives plus false negatives. Looks very hi-fi, but what it means is true positives divided by row total. So the recall is 46 divided by true positives plus false negatives. This is false negatives. For this class, this is false negative, right? So yeah, so it is 46 plus 38 back to 84. That comes to around 55%. Hey. It's coming like 55, 54%, right? That is like tossing a coin, heads or tails. You don't need a model for this. Right? So to get this kind of accuracy, you don't need a model. You can just toss a coin and say diabetic, non-diabetic. That is what this is. So overall looks great, but don't get fooled by this. What is important is this, but this is what we expected because this is represented very poorly, the diabetic class. This is important for us. Look at the recall for the non-diabetic class. Non-diabetic class, the recall is 132 by 147. This will come very high, 90%, 80%, 90% roughly round. So the recall for the non-diabetic class is very high. Recall for the diabetic class is extremely poor. But that's what you should expect. We wanted the reverse. So that's what will happen when you have situations like this. Okay? There is no way you can get a very good model when the individual attributes are poor attributes and the classes are underrepresented. You can't do it. So the magic happens in the data. How do you prepare your data for analytics? That is where the magic is. It is not in the algorithms. Okay? It depends on data preparation. 80% of our project estimated effort in data science goes into preparing the data. Running the algorithm is matter. Then rest around 15 to 20% goes into fine-tuning your model. It goes into that. All right, let's do, there is a function called score. Instead of doing this, I can directly call score, but don't rely on this when you're doing classification. What this function does is, it regenerates the model and then tests it on this test data. It regenerates the model, then compares the test data and this automatically and gives it the score. Okay, so this has nothing to do with confusion matrix. You can actually run this and say remove the hash, run it. It should give you the score. Model is not defined. Why? What spelling mistake? Oh, I have not executed. I'm just showing you this. Okay. I have not executed these lines. So it gives you overall score, but overall score is not reliable, so don't depend on this.
I want to introduce you to Great Learning Academy, a free learning initiative by Great Learning, where you can access over 200 plus courses with 1,000 plus hours of free content on trending high demand domains such as data science, machine learning, artificial intelligence, programming, cloud computing, digital marketing, DevOps, management, and many more, absolutely free. Award-winning academicians and leading industry experts design these courses. You can also get a free certificate of completion when you enroll and complete these free courses. You also get access to the presentations, code, notebooks, datasets, and quiz. We have courses in English and Hindi to give you the best learning experience in the language you're comfortable with. Check out the description of this video to access the relevant course on Great Learning Academy. So what are you waiting for? Register now and start your learning journey today.